Science has already written the obituary for a star that has never existed. Its physics is settled, its structure is mapped, its final moments are predicted down to the degree we have given it a name, a place in stellar evolution, and a destiny more patient than anything else in the known universe. And yet, after all that certainty, after decades of equations and simulations and careful modeling, not a single black dwarf has ever been seen. Not one. Not anywhere in the 13.8 billion year history of our cosmos. This is not a failure of telescopes. It is not a gap in our understanding. It is something stranger. Black dwarfs are real in every sense that matters to physics. The math works. The cooling curves hold. The endpoint is inevitable, but the universe is simply too young for them to exist yet. A white dwarf takes more than 10 quadrillion years to go dark. That is not a typo, 10 with 15 zeros behind it. A time span so vast, it makes the age of galaxies look like the blink of an eye. These objects are not waiting to be discovered, they are waiting to happen. And they are not alone in their strangeness. Along the way to absolute darkness, white dwarfs crystallize into planet-sized diamonds, radiate away heat slower than anything else in nature, and in some predictions, explode in the final supernovae the universe will ever witness, trillions upon trillions of years after the last star dies. This is the story of a cosmic inevitability with no present tense, a star with a name, a fate, and no form. The longest wait in the history of time itself, and it has already begun. Welcome to Magnetic Space. If you're new here, please subscribe. We make these documentaries every day, and honestly, we'd love to have you along for the ride. Before we begin, tell us in the comments where you're watching from and what time it is there. Now settle in. This is going to be a good one. There is a star in the night sky that will outlive the universe as we know it, not because it's still burning, but because it has run out of ways to die. It will sit in the dark, cooling, waiting, ticking down toward a temperature so close to absolute zero that the word cold stops meaning anything. And even after every galaxy has flown beyond the horizon, after every black hole has evaporated, after the last photon from the last dying star has stretched into nothingness, this object will still be there, glowing faintly with the memory of heat it once had, except you will never see it. No human ever will. Because the universe, at 13.8 billion years old, is far too young for this kind of star to exist. This is not speculation. This is thermodynamics. This is what happens when you take the life cycle of a star, run it to completion, and keep going. Most stars die loudly. They explode, collapse, or puff off their outer layers into space like cosmic dandelions. A handful die differently. They shut down, freeze, and refuse to leave. And the final stage of that death, the absolute end of the line, is something called a black dwarf, a stellar corpse so cold and so dark that it emits no light, no heat, no radiation of any kind, just a ball of crystallized carbon and oxygen the size of Earth, drifting through the void like a tombstone with no name. The problem is that getting to that stage takes time. Not millions of years, not billions, somewhere in the neighborhood of 10 quadrillion years. That is a 1 with 16 zeros after it. To put that in perspective, the universe has existed for about 14 billion years. If you lined up the entire history of the cosmos from the Big Bang to today and stretched it across a football field, the time required for a single black dwarf to form would circle the Earth about 70,000 times, and that is just for the first one. So when we talk about black dwarfs, we are not talking about something we have observed. We are not even talking about something that exists. We are talking about the inevitable conclusion of a process that has barely begun, a star that cannot exist yet but one day must. Let's back up. Stars do not live forever. That much has been clear since the early 20th century, when physicists started figuring out what makes them shine in the first place. A star is essentially a sustained nuclear explosion held together by its own gravity. At its core, hydrogen fuses into helium, releasing energy in the form of light and heat. That energy pushes outward, balancing the inward crush of gravity. As long as the fuel holds out, the star stays stable. When the fuel runs out, the balance breaks. What happens next depends almost entirely on how massive the star is. If it is big enough, more than about 8 times the mass of our Sun, it will go supernova. The core collapses, rebounds, and the star tears itself apart in an explosion so bright it can briefly outshine an entire galaxy. What is left behind is either a neutron star, a ball of matter so dense that a teaspoon of it would weigh 1 billion tons, or a black hole which needs no introduction. But most stars are not that big. Most stars, including our Sun, fall into a category astronomers call low to medium mass. These stars do not have the weight to trigger a supernova. When they run out of hydrogen, they swell into red giants, bloat to hundreds of times their original size, and then gently shed their outer layers into space. What remains is the core. Hot, dense, no longer fusing anything. This is a white dwarf. White dwarfs are strange objects. They are roughly the size of Earth but contain about as much mass as the Sun. That means they are extraordinarily dense. A sugar cube of white dwarf material would weigh about a ton on Earth. You could fit the entire population of the planet into a volume the size of a refrigerator if you compressed us to white dwarf density. Not that you should try. The matter inside a white dwarf is not like the matter you are used to. It is something called electron-degenerate matter. In normal matter, electrons orbit atomic nuclei in predictable shells. In a white dwarf, the pressure is so extreme that the electrons are squeezed off their orbits entirely. They form a kind of quantum gas that obeys rules laid out by the Pauli exclusion principle, which in plain language says that no 2 electrons can occupy the same quantum state at the same time. This creates a pressure called degeneracy pressure that has nothing to do with temperature or heat. It is purely a product of quantum mechanics, refusing to let the electrons collapse any further. That pressure is the only thing holding a white dwarf up. There is no fusion, no outward radiation, just the stubbornness of electrons refusing to be in the same place at the same time. Gravity pulls inward. Degeneracy pressure pushes outward. The two forces balance, and the star sits there, stable, inert, supported entirely by the fact that quantum mechanics has rules, and those rules cannot be broken. But a white dwarf is not cold, not at first. When it forms, the core temperature can exceed 100,000 Kelvin. That is hotter than the surface of most living stars. The white dwarf glows brilliantly, radiating energy into space. Over time, that energy leaks away. The dwarf cools, and unlike a living star, which generates new heat through fusion, a white dwarf has no way to replace what it loses. It is, as one astronomer put it, a pan that has been taken off the stove. It will cool until it reaches the temperature of its surroundings. In this case, the surrounding temperature is the cosmic microwave background, the faint afterglow of the Big Bang, which currently sits at about 3 Kelvin. That is roughly minus 270 degrees Celsius, just a hair above absolute zero. The process is not fast. White dwarfs are incredibly good at holding on to heat. They have no atmosphere to speak of, no convection, no easy way for thermal energy to escape. The only mechanism available is radiation. Photons slowly seep out from the surface, carrying energy with them, one quantum at a time. The dwarf cools at a glacial pace. For the first few billion years, it remains hot enough to glow visibly. It starts out white, hence the name, then fades to yellow, then orange, then red as the surface temperature drops. Eventually, it dims below the threshold of visible light and enters the infrared. It is still radiating, still leaking energy, but now in wavelengths the human eye cannot see. After about 10 billion years, the white dwarf has cooled to a few thousand Kelvin. It is no longer white, it is barely glowing. But it is still warm by cosmic standards. The core, insulated by kilometers of densely packed matter, retains heat far longer than the surface. The cooling slows, the process stretches, and the star enters a phase of almost unimaginable patience. The math on this is surprisingly straightforward once you account for the lack of internal heat sources. A white dwarf loses energy according to the Stefan Boltzmann law, which describes how objects radiate heat based on their surface temperature. The rate of cooling slows exponentially as the temperature drops. Early on, a white dwarf can cool by thousands of degrees in a billion years. Later, it might take 1 trillion years to drop by a few hundred degrees. The curve flattens, time stretches, and the final approach toward the ambient temperature of the universe, toward that 3 Kelvin baseline, becomes a process measured not in billions of years but in quadrillions. Current estimates place the time required for a white dwarf to cool to the point where it stops radiating in any meaningful way at around 10 quadrillion years. That is 10 to the 15th power, 1,000 times longer than the universe has existed. By the time the first black dwarf forms, the cosmic microwave background will have cooled to nearly zero. The last stars will have burned out trillions of years earlier. Galaxies will have long since dissolved, their stars flung into intergalactic space by gravitational interactions or swallowed by the supermassive black holes at their centers. The universe will be a cold, dark, nearly empty place, and somewhere in that void, a single white dwarf will tick over into the final category. Black dwarf, a star that emits no light. A star that is, for all practical purposes, dead. We have found plenty of white dwarfs. There are billions of them in our galaxy alone. Some are relatively young, still glowing hot and bright. Others are ancient, cool, faint, sitting at the edge of detectability. The coolest white dwarf ever discovered, an object with the catalog name WD0555-038, has a surface temperature of about 3,900 Kelvin. That is cool by white dwarf standards, but still hot enough to melt titanium. It is thought to be roughly 11 billion years old, meaning it has been cooling since before the Earth formed, and it is still a long way from becoming a black dwarf. No one has ever seen a black dwarf. No one ever will in any currently conceivable future. The universe simply has not been around long enough. The oldest white dwarfs we know of are still radiating in the infrared. They are still warm. They are still, in a technical sense, alive. The first true black dwarf, the first stellar remnant cold enough to have reached thermal equilibrium with the void, will not appear for at least another 10 quadrillion years, and that is a conservative estimate. Some models push the timeline even further. There is a wrinkle in the cooling process that makes the whole thing even stranger. As a white dwarf cools, the carbon and oxygen inside it begin to crystallize. This is not a metaphor. The atoms, no longer vibrating with enough thermal energy to stay disordered, lock into a rigid lattice structure. The core of the white dwarf becomes a single enormous crystal, a diamond essentially the size of a planet. This crystallization releases a small amount of latent heat, the same way water releases heat when it freezes into ice. That extra energy slows the cooling process even further, adding billions of years to the timeline. The star is quite literally freezing solid from the inside out, and that freeze is taking longer than the current age of the universe. Astrophysicists have built detailed models of this process. They account for the composition of the white dwarf, its mass, its rotation, the thickness of its outer hydrogen and helium layers. They simulate the gradual loss of thermal energy, the formation of the crystal core, the slow fade from visibility into darkness. Every model arrives at the same conclusion. Black dwarfs are real, they are inevitable, and they are waiting in a future so distant that the word future stops making intuitive sense. There is one more twist. If a hypothetical class of particles called weakly interacting massive particles, or WIMPs, actually exists, the timeline changes. WIMPs are a candidate for dark matter, the invisible substance that makes up most of the mass in the universe. If they are real, and if they interact with ordinary matter even weakly, they could be captured by the intense gravitational field of a white dwarf. Over time, WIMPs would accumulate in the core, annihilate with each other, and release energy. That energy would keep the white dwarf warm, potentially for up to 10 to the 25th power years. That is 10 septillion years. A timeline so absurdly long that even cosmologists struggle to find useful comparisons for it. At that point, you are no longer talking about the age of the universe. You are talking about a span of time during which the universe itself might undergo phase transitions we cannot currently predict. But even if WIMPs do not exist, even if the cooling proceeds exactly as the simplest models predict, the result is the same. A black dwarf is not something you will ever point a telescope at and observe. It is not something humanity will ever directly detect. It is a conclusion written into the equations that govern heat, light, and time. A star that can only exist in a universe far older and far colder than the one we live in now. A remnant of a process that has only just begun, and yet somewhere out there the clock is ticking. Every white dwarf in the galaxy is cooling. Every second, a tiny fraction of their stored thermal energy radiates into space. The process is slow, patient, inevitable, and in a future almost too distant to comprehend, the first of them will cross the threshold. The last light will fade, the surface will cool to match the void, and the universe will have its first black dwarf. But before it gets there, before that final cold silence, the white dwarf has a long, strange journey ahead of it. One that begins not with darkness, but with an ember, a faint, stubborn glow that refuses to die. And that is where we go next. A white dwarf begins its life as a funeral, not the quiet kind, the messy kind, where the deceased refuses to stay in the casket and instead throws half their body mass into space at thousands of kilometers per second. What remains, the core, sits alone in the aftermath, exposed to the universe for the first time in billions of years, and that core is still screaming hot. When a star like our Sun exhausts the hydrogen in its core, fusion stalls. The outward pressure from nuclear reactions drops, and gravity takes over. The core contracts. The outer layers, no longer supported, begin to fall inward. That compression heats the core enough to ignite helium fusion, a secondary fuel source that buys the star a few more million years. The energy released is so intense that the outer envelope of the star expands outward, swelling to hundreds of times its original size. The star becomes a red giant. Our Sun, when it reaches that phase in about 5 billion years, will expand past the orbit of Mercury, possibly past Venus, and turn Earth into a charred cinder drifting through the outer atmosphere of a dying star. During this phase, the core continues to fuse helium into carbon and oxygen, but fusion is an uphill battle. Each step up the periodic table requires higher temperatures and pressures. Hydrogen fuses at around 10 million Kelvin. Helium needs 100 million. Carbon and oxygen, the next logical steps, require several 100 million Kelvin. A star the mass of our Sun never gets there. It simply does not have enough gravitational weight to compress the core to those temperatures. Fusion stops at carbon and oxygen. The reactions shut down. The core, now inert, begins to contract under its own gravity. Meanwhile, the outer layers, no longer bound tightly to the core, drift away. They form what astronomers call a planetary nebula, a glowing shell of gas expanding into space. The name is a historical accident. Early astronomers thought these objects looked like planets through their crude telescopes. They were wrong, but the name stuck. What is left behind is the core, roughly the mass of the Sun, compressed into a sphere about the size of Earth. This is a white dwarf. No fusion, no nuclear reactions, just a ball of carbon and oxygen held together by something that is not heat, not pressure in the traditional sense, but a purely quantum mechanical effect that refuses to let the star collapse any further. The key to understanding a white dwarf is understanding what happens to matter when you squeeze it hard enough that normal physics starts to break. In ordinary matter, atoms are mostly empty space. The nucleus sits at the center, a tiny dense knot of protons and neutrons, and the electrons orbit far outside in probabilistic clouds. The distance between the nucleus and the electrons is enormous compared to the size of the particles themselves. If you scaled an atom up so that the nucleus was the size of a marble, the electrons would be orbiting kilometers away. Most of what you think of as solid is actually just electromagnetic forces keeping other atoms at a distance. When you sit in a chair, you are not actually touching it. The electrons in your body are repelling the electrons in the chair. You are hovering, held up by forces operating at scales far too small to see. In a white dwarf, that empty space gets crushed out. The gravitational pressure is so extreme that the electron clouds are stripped away from the atomic nuclei. The electrons are squeezed into a dense sea, packed so tightly that they start behaving less like individual particles and more like a fluid governed by quantum rules. This is electron-degenerate matter. The term sounds abstract, but it describes something very specific. In quantum mechanics, no two fermions, a class of particles that includes electrons, can occupy the same quantum state in the same place at the same time. This is the Pauli exclusion principle, and it is not a guideline. It is a law written into the structure of reality. Push two electrons into the same quantum state and the universe pushes back, hard. That pushback creates a pressure called electron degeneracy pressure. It has nothing to do with temperature. You could cool a white dwarf to absolute zero and the pressure would not change. It is purely a consequence of quantum mechanics refusing to let the electrons be compressed beyond a certain point. The electrons, packed into the lowest available energy states, form a kind of quantum scaffolding that holds the star up. Gravity pulls inward, degeneracy pressure pushes outward. The two forces balance, and the white dwarf sits there, stable, inert, held up by nothing more than the stubbornness of quantum mechanics. The density this creates is difficult to overstate. A white dwarf, with the mass of the Sun compressed into the volume of Earth, has an average density of about 1 million grams per cubic centimeter. A sugar cube of white dwarf material would weigh roughly 1 metric ton. A teaspoon would weigh about as much as an elephant. If you could somehow stand on the surface of a white dwarf, which you could not because the gravity would flatten you into a layer of atoms 1 molecule thick, you would weigh roughly 200,000 times what you weigh on Earth. A 100-kilogram person would weigh 20 million kilograms. Your bones would not just break. They would cease to exist in any recognizable form. You would not fall. You would become part of the surface, a smear of carbon and trace metals added to the crust. The composition of a white dwarf depends on what the star was fusing before it died. Most white dwarfs are made primarily of carbon and oxygen, the end products of helium fusion in stars like our Sun. Some contain traces of heavier elements, neon, magnesium, silicon, left over from more advanced fusion stages in slightly more massive stars. A handful of white dwarfs are made mostly of helium, remnants of stars that never got hot enough to fuse helium in the first place, or binary systems where one star stripped material from its companion before it could complete its life cycle. And in rare cases, white dwarfs can contain traces of hydrogen or helium in thin outer layers, material that never fully mixed into the core during the star's red giant phase. But the bulk of a typical white dwarf is carbon and oxygen arranged in a dense plasma at the surface and, as it cools, a crystalline lattice deeper inside. We will come back to that crystallization later. For now, the important part is that the material is locked in place. It is not flowing, it is not convecting in the way a living star's interior does. It is sitting there, slowly losing the heat it accumulated over billions of years of fusion. When a white dwarf first forms, it is extraordinarily hot. The surface temperature can range from 10,000 to over 100,000 Kelvin, depending on the mass and the specifics of the star that produced it. For comparison, the surface of our Sun sits at around 5,700 Kelvin. A freshly minted white dwarf is far hotter. It glows brilliantly, often brighter than the planetary nebula surrounding it. That heat is not coming from fusion. There are no nuclear reactions left. The heat is residual, left over from the gravitational compression that occurred during the star's final collapse. Think of it like a pan that has just been taken off a stove. The pan is still hot, but it is not generating new heat. It is radiating away the energy it absorbed while it was being heated. A white dwarf is doing the same thing, but on a scale that stretches across billions of years. The process by which a white dwarf loses that heat is straightforward in principle, but glacially slow in practice. The star radiates energy into space in the form of photons. Early on, when the surface is still tens of thousands of Kelvin, those photons are in the ultraviolet and visible range. The white dwarf glows white, hence the name. Over time, as the surface cools, the peak wavelength of the emitted light shifts toward the red end of the spectrum. The dwarf fades from white to yellow to orange to red. Eventually, it cools below the threshold of visible light entirely and enters the infrared. At that point, it is no longer a white dwarf in the literal sense. It is a red dwarf, though astronomers do not use that term because red dwarf already refers to a different kind of object, a small, cool, hydrogen-burning star. Instead, they just keep calling it a white dwarf, even after it stops being white. Astronomy is full of these naming quirks. You get used to it. The rate at which a white dwarf cools is governed by the Stefan-Boltzmann law, which describes how objects radiate energy based on their surface area and temperature. The power radiated is proportional to the fourth power of the temperature. That means a white dwarf that is twice as hot radiates 16 times as much power. Early in its cooling phase, when the surface is still extremely hot, the dwarf loses energy relatively quickly. Over the first billion years, a typical white dwarf might cool from 100,000 Kelvin down to around 20,000. That is a dramatic drop, but the cooling does not proceed linearly. As the temperature falls, the rate of energy loss slows. By the time the surface temperature has dropped to 10,000 Kelvin, the cooling rate has slowed significantly. Drop it to 5,000 and the rate slows even more. The curve flattens, time stretches. And the final approach toward the ambient temperature of the universe becomes a process measured not in millions or billions of years, but in trillions. There is another factor slowing the cooling. White dwarfs are not perfect blackbodies. They have thin outer layers of hydrogen and helium, remnants of the original star's envelope that did not get blown away during the red giant phase. These layers act as insulators, trapping heat inside the star and slowing the rate at which it can radiate into space. The thicker those layers, the slower the cooling. Some white dwarfs have almost no hydrogen or helium left. Their surfaces are exposed carbon and oxygen, and they cool faster. Others have relatively thick envelopes, and they hold onto their heat for much longer. The composition and structure of those outer layers can add billions of years to the cooling timeline. In the very early stages, there is also convection. The outer layers of a newly formed white dwarf can still be hot and diffuse enough for heat to circulate through convective currents, the way boiling water circulates in a pot. Hot material rises, cools at the surface, and sinks back down. This process helps distribute heat from the interior to the surface, where it can radiate away more efficiently. But convection only works when there is a significant temperature gradient and when the material is fluid enough to move. As the white dwarf cools and the outer layers become more degenerate, convection slows and eventually stops. The star transitions to purely radiative cooling, where heat moves outward only through the emission and absorption of photons. This is slower, much slower. One way to visualize the scale of this cooling process is to think about the oldest white dwarfs we have actually observed. Astronomers have found white dwarfs that are estimated to be 10 to 12 billion years old, nearly as old as the universe itself. These are among the faintest objects we can detect. Their surface temperatures have dropped to around 3,000 to 4,000 Kelvin. That is cooler than the surface of the coolest red dwarf stars, which sit at around 2,500 Kelvin. And yet, even after 12 billion years of cooling, these ancient white dwarfs are still radiating in the infrared. They are still warm. They are nowhere near becoming black dwarfs. The process is only about halfway complete, if that. The internal structure of a white dwarf is worth pausing on because it is stranger than the smooth, uniform sphere you might picture. The core is the hottest part, insulated by layers of cooler material above it. In a freshly formed white dwarf, the core can be tens of millions of Kelvin, even while the surface has already cooled to a few tens of thousands. That temperature gradient drives the outward flow of heat, but the dense, degenerate matter conducts heat poorly compared to ordinary matter. Heat moves through a white dwarf like sound through molasses, slowly, reluctantly, one photon at a time. The result is that the core stays hot for an extraordinarily long time, even as the surface cools and dims. By the time the surface has cooled to a few thousand Kelvin, the core might still be several million degrees. That heat is locked inside, trickling outward at a rate so slow that it makes geological processes on Earth look frantic by comparison. There is a specific moment in a white dwarf's cooling history that marks a turning point. As the temperature in the core drops below a certain threshold, the carbon and oxygen atoms which have been vibrating in a dense plasma begin to lose enough thermal energy that they start locking into fixed positions. The material crystallizes. It forms a solid lattice, a single enormous crystal the size of a planet. This is not a metaphor. The core of a cooling white dwarf quite literally becomes a crystal. And because crystallization releases latent heat, the same way water releases heat when it freezes into ice, the process of solidifying the core adds a pulse of energy back into the system. That energy has to radiate away before the cooling can continue. The result is that crystallization acts as a speed bump in the cooling timeline, adding billions of years to the process. A white dwarf, that would have cooled to a given temperature in, say, 8 billion years might take 10 or 11 billion if you account for the energy released during crystallization. The crystal does not make the star warmer, it just slows the rate at which it gets colder. For a long time, this crystallization process was purely theoretical. Physicists predicted it based on the known behavior of dense matter, but no one had directly observed it. That changed in 2019 when a team using data from the European Space Agency's Gaia satellite identified a population of white dwarfs that appeared to be sitting at a specific brightness and color for longer than models predicted. The delay was consistent with the energy release expected from crystallization. The core was freezing, and the freeze was taking time. This was the first direct observational evidence that white dwarfs really do crystallize as they cool. The physics textbooks had been right. The cores were turning into diamonds. The term diamond is admittedly a bit misleading. When most people hear diamond, they picture a clear gemstone you might find in a ring. A white dwarf's crystallized core is not transparent. It is not cut and polished. It is a solid lattice of carbon and oxygen atoms packed into a degenerate state under pressures millions of times higher than anything on Earth. But the structure is the same. The atoms are arranged in the same repeating geometric pattern that defines a diamond crystal. If you could somehow extract a chunk of it and bring it back to normal pressure and temperature, which you absolutely could not because the moment you released the pressure it would explosively decompress and probably vaporize, it would be chemically indistinguishable from diamond. Same lattice, same bonds, just formed under conditions so extreme that calling it a diamond feels like calling the sun a campfire. Technically accurate, wildly insufficient. As the white dwarf continues to cool, the crystallization front moves outward from the core. The innermost regions solidify first. Then, as the temperature drops further, the crystal grows, layer by layer, consuming the surrounding material. The process is not fast. It can take billions of years for the entire core to freeze. And even after it has fully crystallized, the white dwarf is still hot. The crystal is just a lattice of atoms locked in place. The atoms are still vibrating. They still have thermal energy. They are just no longer free to move around. The cooling continues. The vibrations slow. The temperature drops, and the white dwarf inches closer to the final stage of its existence. But that final stage is still unimaginably far away. Even the oldest, coldest white dwarfs we have found are still glowing faintly in the infrared. They are still radiating. They are still, in a technical sense, alive. They have not yet crossed the threshold into true darkness. That threshold, the point at which the white dwarf cools to the temperature of the cosmic microwave background and stops emitting any detectable radiation, is where the black dwarf begins. And the timeline for reaching that point stretches so far into the future that it makes the current age of the universe look like a rounding error. For now, though, the white dwarf is an ember. Cooling, yes. Fading, certainly. But still burning with the residual heat of a star that once fused hydrogen into helium, that once held planets in orbit, that once perhaps warmed a world where life looked up at a sky and wondered what lay beyond. That heat is all that remains, and it is taking its time leaving. But beneath that glow, deep in the core where the temperature has finally dropped low enough, something remarkable is happening. The atoms are locking into place, the lattice is forming, the star is crystallizing into a structure so perfect, so geometrically precise, that it rivals anything nature has ever built. And that crystal, that vast planetary diamond growing silently in the heart of a dead star, is where we turn next. The first time astronomers seriously considered the idea that a white dwarf could turn into a giant crystal, The reaction was not excitement, it was skepticism. Crystals were things you found in caves or grew in high school chemistry class. They were not what happened to the core of a dead star, sitting in the middle of space, radiating away the last remnants of heat from a fusion reaction that ended billions of years ago. The idea sounded less like astrophysics and more like science fiction written by someone who had never taken a physics course. The problem was that the math said otherwise, and in physics, the math tends to win arguments. The prediction came out of the same body of work that explained how white dwarfs could exist at all. In the 1960s, physicists were working through the behavior of matter under extreme pressures, trying to understand what happens when you pack stellar mass into planetary volumes. The equations describing electron degeneracy pressure were well established by then. Subramanian Chandrasekhar had already worked out the maximum mass a white dwarf could support before collapsing into a neutron star, a limit that now bears his name. But the question of what happened inside the white dwarf as it cooled had not been fully explored, and when researchers started running simulations of cooling white dwarfs, they kept running into the same result. At a certain temperature, the carbon and oxygen ions in the core would lose enough thermal energy that they would stop behaving like a hot plasma and start behaving like a solid. They would crystallize. The theory was straightforward. A white dwarf is made mostly of carbon and oxygen nuclei swimming in a sea of degenerate electrons. At high temperatures, those nuclei have enough kinetic energy to move around freely. They vibrate, collide, bounce off each other in a chaotic dance governed by thermal motion. But as the white dwarf cools, the average energy of those nuclei drops. Eventually, the thermal energy becomes low enough that the electrostatic forces between the positively charged nuclei start to dominate. Those forces want to arrange the nuclei into the lowest energy configuration possible. And the lowest energy configuration for a dense collection of charged particles is a regular repeating lattice, a crystal. This is the same process that happens when water freezes into ice. Liquid water is a chaotic collection of molecules bouncing around, held together loosely by hydrogen bonds. Cool it down, and the molecules lose kinetic energy. At 0 degrees Celsius, the hydrogen bonds take over, locking the molecules into a rigid hexagonal lattice. The water becomes ice. The transition releases latent heat because forming those bonds is energetically favorable. The same thing happens in a white dwarf, just at vastly higher densities and temperatures. The carbon and oxygen nuclei, once free to move, lock into a crystalline structure. The material transitions from a dense plasma to a solid lattice. The star quite literally freezes. The critical temperature at which this happens depends on the density of the material and the types of nuclei involved. For a typical white dwarf composed mostly of carbon and oxygen, crystallization begins when the core temperature drops below about 10 million Kelvin. That might sound hot. It is hot by everyday standards. But for a white dwarf that started its cooling phase at temperatures exceeding 100 million Kelvin, 10 million is cold. It is the point where the thermal energy of the nuclei is no longer strong enough to overcome the electrostatic attraction pulling them into an ordered arrangement. The structure that forms is determined by the charge and mass of the nuclei. Carbon and oxygen, the two most common elements in a white dwarf, both form what is known as a body-centered cubic lattice under these conditions. Picture a cube with an atom at each corner and one atom in the very center. Repeat that structure in all directions, stacking cube after cube after cube, and you get the internal architecture of a crystallized white dwarf core. The lattice extends for thousands of kilometers in every direction. It is not a small crystal. It is not a collection of many crystals. It is a single, coherent, unified crystal structure the size of a planet. This is where the diamond comparison comes from. Diamond, the hardest naturally occurring material on Earth, is made of carbon atoms arranged in a specific crystalline lattice. The arrangement is slightly different from what forms in a white dwarf. Diamond has a face-centered cubic structure, but the underlying principle is the same: carbon atoms locked into a rigid, repeating geometric pattern. In a white dwarf, the carbon nuclei are doing exactly that. The fact that the material is also under pressures millions of times higher than anything on Earth and is mixed with oxygen and is held together by electron degeneracy pressure does not change the fundamental nature of the structure. It is a crystal, a diamond more or less the size of Earth. The realization that white dwarfs could crystallize had immediate implications for how they cooled. Crystallization is not a smooth, continuous process. It is a phase transition, the same kind of transition you see when water freezes or when steam condenses into liquid. And phase transitions release energy. When the carbon and oxygen nuclei lock into the crystalline lattice, they move into a lower energy state. The difference in energy between the disordered plasma and the ordered crystal has to go somewhere. It gets released as heat. This is latent heat, the same concept that keeps a glass of ice water at 0 degrees Celsius even as the ice melts. The energy you add to the glass does not raise the temperature. It breaks the bonds holding the water molecules in the ice structure. Only after all the ice has melted does the temperature start to rise. The reverse happens when water freezes. The temperature stays constant while the liquid turns to solid, and the energy released by forming those bonds warms the surrounding environment slightly. In a white dwarf, the crystallization process releases enough latent heat to slow the cooling significantly. The star does not get hotter, it just takes longer to get colder. Models suggest that this delay can add 1 to 2 billion years to the cooling timeline, depending on the mass and composition of the white dwarf. For a long time, this was all theoretical. No one had directly observed a white dwarf crystallizing. The effect was subtle, buried in the cooling curves of stars that were already faint and difficult to measure. Astronomers knew where to look, but the data was not precise enough to confirm the prediction. That changed with the Gaia satellite. Gaia, launched by the European Space Agency in 2013, is a space observatory designed to map the positions, distances, and motions of more than 1 billion stars in our galaxy. It is, by most measures, the most ambitious stellar census ever attempted. And one of the side benefits of mapping 1 billion stars is that you end up with extremely precise data on a lot of white dwarfs. By 2019, Gaia had catalogued enough white dwarfs to allow astronomers to look for patterns in their cooling behavior, and they found something odd. A team led by Pierre-Emmanuel Tremblay at the University of Warwick analyzed the Gaia data and noticed a pile-up. A larger than expected number of white dwarfs were sitting at a specific range of brightness and color, corresponding to a surface temperature of roughly 8,000 to 10,000 Kelvin. If white dwarfs cooled smoothly and continuously, you would expect the distribution to be even. Stars would spend roughly the same amount of time at every temperature on their way down to zero. But the data showed a cluster. White dwarfs were lingering at that temperature range longer than they should have. The explanation was crystallization. At around 10 million Kelvin in the core, the carbon and oxygen began to solidify. The latent heat released by that process slowed the cooling rate, causing the white dwarfs to spend extra time at the corresponding surface temperature before continuing their descent. The pile-up in the Gaia data was exactly where the models predicted it should be. The delay was consistent with 1 to 2 billion years of additional cooling time. The white dwarfs were crystallizing, just as the theory said they would. This was the first direct observational evidence that white dwarf cores turn into crystals. The prediction, made decades earlier based on the physics of dense matter, had been confirmed. The cores were freezing. The stars were turning into diamonds. It is worth pausing to appreciate the scale of what is happening here. A white dwarf has roughly the mass of the Sun, about 2 × 10⁻30th power kilograms. Most of that mass is in the core, which is now crystallizing into a single unified structure. If you could somehow weigh the crystallized portion of a typical white dwarf, it would come in at somewhere around 10⁻30th power kilograms of solid carbon and oxygen arranged in a perfect lattice. For comparison, the entire Earth weighs about 6 × 10⁻24th power kilograms. The crystallized core of a white dwarf is roughly 1,000,000 times more massive than our entire planet, and it is all one crystal. There is no naturally occurring object in the universe that even comes close to this scale. The largest single crystals found on Earth are gypsum formations in the Cave of Crystals in Mexico, some of which are over 10 meters long and weigh several tons. These are geological oddities, formed over tens of thousands of years under very specific conditions. A white dwarf's crystallized core is not a geological oddity. It is the inevitable result of cooling a dense stellar remnant over billions of years. It is what happens when you let gravity, quantum mechanics, and thermodynamics run their course without interruption. The composition of the crystal depends on what the star was made of before it died. Most white dwarfs are primarily carbon and oxygen, the products of helium fusion, but some contain significant amounts of neon, magnesium, or silicon left over from more advanced fusion stages in slightly more massive progenitor stars. These heavier elements can also crystallize, and they do so at slightly different temperatures. In a mixed composition white dwarf, you can end up with a layered structure, a core of one type of crystal surrounded by a shell of another. The exact details depend on the cooling history and the distribution of elements in the star before it became a white dwarf. There is also the question of impurities. No white dwarf is made purely of carbon and oxygen. There are always trace amounts of other elements mixed in: hydrogen, helium, neon, iron, whatever was present in the original star's composition. In an ordinary crystal, impurities disrupt the lattice. They create defects, weak points where the structure is not perfectly ordered. In a white dwarf, the densities are so extreme that most of these impurities get incorporated into the lattice without disrupting it. The crystal is not chemically pure in the way a laboratory-grown diamond might be, but it is structurally sound. The lattice extends unbroken across thousands of kilometers. Defects exist, but they are rare and localized. The process of crystallization also affects the way heat moves through the white dwarf. In a plasma, heat is transported primarily through radiation and, to a lesser extent, conduction by the degenerate electrons. In a solid crystal, heat transport changes. The lattice vibrations, called phonons, become the dominant mechanism for moving thermal energy from the hot interior to the cooler surface. Phonons are just quantized sound waves, ripples in the crystal lattice that carry energy. In a perfectly ordered lattice, phonons can travel very efficiently, but white dwarf crystals are not at zero temperature. The atoms are still vibrating. Those vibrations scatter the phonons, reducing their efficiency. The result is that thermal conductivity in a crystallized white dwarf is lower than it would be in a plasma at the same density. The crystal insulates the core, trapping heat inside and slowing the rate at which it can radiate away into space. This creates a kind of feedback loop. The crystallization releases latent heat, which slows the cooling. The crystal then acts as an insulator, slowing the cooling even further. The combined effect is that the final stages of white dwarf cooling, the stretch from 10 million Kelvin in the core down to near zero, take far longer than the earlier stages. The star is still cooling. It is just doing so at a pace that makes glaciers look impatient. One of the more interesting predictions to come out of crystallization models is that the process does not happen uniformly throughout the core. It starts at the very center, where the density is highest and the temperature drops first. The crystallization front then moves outward, layer by layer, as the surrounding material cools below the critical temperature. The result is a white dwarf with a solid crystalline core surrounded by a shell of still liquid plasma, surrounded in turn by the thin outer layers of hydrogen or helium that insulate the whole structure. Over billions of years, the crystallization front advances outward, consuming more and more of the star's mass until eventually the entire core is solid. But even then, the outer layers remain liquid or gaseous. The white dwarf never fully solidifies. It is a crystal wrapped in a thin envelope of matter that refuses to freeze. There is a wrinkle in all of this that has to do with rotation. White dwarfs, like most stars, spin. They inherited their rotation from the original star that collapsed to form them. As the star contracts, conservation of angular momentum speeds up the rotation, the same way a figure skater spins faster when they pull their arms in. A typical white dwarf rotates once every few hours to once every few days, depending on its history, and as the core crystallizes, that rotation can create stresses in the lattice. The outer layers, still liquid, rotate at a slightly different rate than the solid core. The boundary between the two, called the crystallization front, experiences shear forces. Over very long timescales, those forces can cause the lattice to crack or deform. Models suggest that this might create something analogous to tectonic activity, shifts in the crystal structure that release stored energy. These would not be earthquakes in the traditional sense. They would be starquakes, sudden rearrangements of a planetary-scale crystal lattice under tidal and rotational stress. The energy released would be small compared to the total thermal energy of the white dwarf, but it would be detectable in principle if we had instruments sensitive enough to watch for it. There is also a potential connection between crystallization and the magnetic fields observed in some white dwarfs. About 10% of white dwarfs have strong magnetic fields, ranging from a few thousand to several billion gas. For comparison, Earth's magnetic field is about half a gas. A refrigerator magnet is about 100 gas. A white dwarf with a billion gas magnetic field is strong enough to distort the shapes of atoms, stretching their electron clouds into elongated needles aligned with the field. The origin of these fields is not fully understood. One possibility is that they are fossil fields, remnants of the magnetic field in the original star, amplified by the collapse. Another possibility is that they are generated by dynamo processes in the liquid outer layers of the white dwarf. But there is a third possibility, one that has gained traction in recent years. The crystallization process itself might generate or amplify magnetic fields. As the crystal forms, impurities and charged particles can be expelled from the lattice, creating charge separations and currents that generate magnetic fields. If this process occurs unevenly across the crystallization front, it could produce complex tangled field structures that persist for billions of years. The observational evidence for white dwarf crystallization is still being refined. The Gaia data provided the first clear signal, but Gaia measures brightness and color, not temperature directly. To really pin down what is happening inside these stars, astronomers need spectroscopy. They need to measure the light coming from the white dwarf in fine detail, looking for signatures of elements, densities, and temperatures that can be compared against models. This is difficult because cool white dwarfs are faint, very faint. By the time a white dwarf has cooled to the point where its core is mostly crystallized, its surface temperature has dropped below 5,000 Kelvin. At that temperature, it emits most of its light in the infrared, and its total luminosity can be less than 1/10,000th that of the Sun. Detecting these objects at all requires large telescopes with sensitive infrared detectors. Measuring their spectra in enough detail to infer the internal structure requires even more time and precision. Despite these challenges, progress is being made. Surveys like the Sloan Digital Sky Survey and its successors have identified thousands of cool white dwarfs, some with surface temperatures as low as 3000 Kelvin. Follow-up studies with telescopes like the Very Large Telescope in Chile and the Hubble Space Telescope have provided spectra for a handful of the coolest examples. And in every case where the data is good enough to compare against models, the observations line up with the predictions. The cooling rates, the colors, the luminosities, all of it is consistent with cores that are partially or fully crystallized. The coolest white dwarf ever found, as of the latest surveys, has a surface temperature of around 3900 Kelvin. That is cooler than the surface of the coolest red dwarf stars, which bottom out at around 2500 Kelvin. This white dwarf, catalogued as WD 0555-038, is estimated to be roughly 11 billion years old. It has been cooling for nearly as long as the universe has existed, and based on its temperature and luminosity, models suggest that its core is almost entirely crystallized. The carbon and oxygen inside have locked into a solid lattice. The latent heat has been released. The crystallization is complete. What remains is a slowly cooling crystal, insulated by a thin shell of plasma and hydrogen, radiating the last dregs of its thermal energy into the void. Even so, this white dwarf is still warm. It is still glowing, albeit faintly, in the infrared. It is not a black dwarf. It will not become a black dwarf for trillions of years. The crystallization is only one step in the cooling process, not the end. The crystal can still hold heat. The atoms in the lattice are still vibrating. The star is still radiating. It is just doing so at a pace that defies human intuition. One of the more poetic aspects of white dwarf crystallization is what it says about the fate of matter. Diamonds on Earth are rare. They form under very specific conditions, deep underground where pressures are high and temperatures are moderate. They are prized precisely because they are unusual. But in the universe at large, diamonds are not rare at all. Every white dwarf that cools past a certain temperature becomes a diamond, and since white dwarfs are the end state of 97% of all stars, that means the galaxy is filling up with planet-sized diamonds at a rate of roughly 1 per year. By the time the universe is 100 billion years old, there will be trillions of them drifting through space, silent and dark, waiting for nothing. The process is not fast. The journey from a hot white dwarf to a fully crystallized core takes billions of years, but it is inexorable. Every white dwarf that exists today will eventually crystallize. Every star that becomes a white dwarf in the future will follow the same path. Crystallization is not a rare event or a special case. It is the standard outcome for stellar remnants in this mass range. It is what matter does when you give it enough time and pressure and then take away the heat. And once the crystallization is complete, once the core has solidified and the latent heat has radiated away, the white dwarf enters the final, slowest phase of its existence. The phase where it cools from millions of Kelvin down to a few thousand. Then from a few thousand down to a few hundred. Then from a few hundred down to the temperature of the cosmic microwave background, just a few degrees above absolute zero. This is the longest leg of the journey. The part that takes not billions of years but quadrillions. The part where the white dwarf crosses over from a faintly glowing ember into something else entirely. Something cold, something dark, something that no longer deserves to be called a dwarf at all. That transition, the final fade into darkness, is where the cooling process becomes less about physics and more about time. Because at that point, the white dwarf is not doing anything. It is not fusing. It is not crystallizing. It is not convecting or radiating at any meaningful rate. It is just sitting there, slowly leaking the last tiny fractions of its thermal energy into a universe that has grown too cold to notice. And that slow leak, that glacial descent toward absolute zero, is where we go next. The cooling of a white dwarf is not a process you can watch. It is not even a process you can track across multiple human lifetimes or across the entire span of recorded history. It is a process so slow that if you started a stopwatch at the moment the first white dwarf formed in the universe and let it run until now, you would have measured less than 1% of the time required for that star to cool completely. The rest of the journey, the remaining 99%, stretches so far into the future that the numbers stop sounding like time and start sounding like abstract mathematical exercises. And yet, the process is happening. Right now, across the galaxy, billions of white dwarfs are cooling. Slowly, patiently, inevitably, they are leaking their heat into space one photon at a time, and they will continue doing so long after the last star has burned out, long after the last galaxy has dissolved, long after the universe itself has gone cold and dark. The timeline for a white dwarf to cool from its initial temperature down to the ambient temperature of the universe is difficult to state without sounding absurd. The most conservative estimates place the cooling time at around 10 trillion years. That is 10 to the 13th power, a 1 followed by 13 zeros. If you prefer, it is 10,000 billion years. Either way, it is a span of time roughly 700 times longer than the current age of the universe. The universe, as it stands today, is about 13.8 billion years old. A white dwarf needs 10 trillion years to cool completely. The math is not complicated. We are living in a universe that is far too young for black dwarfs to exist. Some models push the timeline even further. If you account for the possibility that dark matter particles, specifically weakly interacting massive particles called WIMPs, actually exist and interact with white dwarfs, the cooling process could stretch to 10 to the 25th power years, that is 10 septillion years. A timeline so absurdly long that even cosmologists struggle to find meaningful comparisons. The current age of the universe, stretched across that span, would be a rounding error. The entire history of stars, galaxies, planets, and life would occupy the first tiny fraction of a percent of that timeline. The rest would be silence. The reason the process takes so long comes down to three factors. First, white dwarfs have no internal heat source. They are not fusing anything. They are not generating new energy. All they have is the residual heat left over from their previous life as a functioning star. That heat is finite. It will run out, but it is also enormous. A white dwarf fresh off the assembly line has a core temperature that can exceed 100 million Kelvin. Even after the surface has cooled to a few tens of thousands of Kelvin, the interior remains scorchingly hot for billions of years. That heat has to go somewhere, and the only way out is radiation. Second, white dwarfs are incredibly dense, and dense objects hold on to heat better than diffuse ones. The material inside a white dwarf is packed so tightly that thermal energy cannot move through it easily. Heat does not flow. It does not convect the way it does in a normal star. Instead, it trickles outward, carried by photons that are constantly being absorbed and re-emitted by the surrounding matter. Each photon takes a random walk through the star, bouncing from atom to atom, gradually working its way toward the surface. The denser the material, the longer that journey takes. In a white dwarf, A single photon generated in the core might take tens of thousands of years to reach the surface and escape into space, and that is just one photon. The star has to radiate away an enormous amount of energy, one photon at a time, before it can cool. Third, as the white dwarf cools, the rate at which it loses energy drops. This is a consequence of the Stefan-Boltzmann law, which governs how objects radiate heat. The power radiated by a hot object is proportional to the fourth power of its temperature. Double the temperature and the object radiates 16 times as much power. Halve the temperature and it radiates only 1/16 as much. For a white dwarf, this means the cooling rate slows dramatically as the surface temperature drops. Early on, when the surface is still tens of thousands of Kelvin, the dwarf can cool by thousands of degrees in a few 100 million years. Later, when the surface has dropped to a few thousand Kelvin, it might take 1 billion years to cool by a few 100 degrees. And in the final stages, when the temperature is approaching the cosmic microwave background at around 3 Kelvin, the cooling rate becomes so slow that it is barely measurable. The star is still radiating, still losing energy, but at a rate so glacial that it makes geological timescales look frantic. The only way a white dwarf loses heat is through radiation, specifically thermal radiation. The surface of the star emits photons across a range of wavelengths determined by its temperature. Hot white dwarfs, those with surface temperatures above 10,000 Kelvin, emit most of their light in the ultraviolet and visible range. They glow white or blue-white, bright enough to outshine many ordinary stars. As they cool, the peak wavelength of their emission shifts toward the red end of the spectrum. The dwarf fades from white to yellow to orange to red. By the time the surface temperature has dropped below 4,000 Kelvin, the star is emitting most of its light in the infrared. It is no longer visible to the naked eye. It has become a dim red glow that fades further with each passing billion years. There is no other mechanism available. A white dwarf does not conduct heat into space the way a hot piece of metal conducts heat into the air. Space is a vacuum. There is no air, no medium to carry the heat away through conduction or convection. The only option is radiation, and radiation is slow. The rate at which energy leaves the star is determined entirely by the surface temperature and the surface area. The surface area does not change. White dwarfs do not expand or contract significantly as they cool. The temperature, however, drops steadily, and as it does, the rate of energy loss slows in lockstep. The result is a cooling curve that starts steep and then flattens into an asymptotic crawl toward zero. One way to visualize the scale of this process is to consider what happens over the first trillion years of cooling. A typical white dwarf starts with a surface temperature of around 20,000 Kelvin. After 1 billion years, it has cooled to about 10,000 Kelvin. After 10 billion years, it is down to around 6,000 Kelvin. After 100 billion years, it might reach 3,000 Kelvin. After 1 trillion years, it could be as low as a few hundred Kelvin. That is still warm. That is still far above the temperature of the cosmic microwave background. The star is still radiating. It is still glowing faintly in the infrared. It has taken 1 trillion years to get to this point, and it still has trillions more to go before it reaches thermal equilibrium with the universe. The final stretch, the last few hundred Kelvin down to 3 Kelvin, takes longer than all the previous cooling combined. This is because the rate of energy loss is now so low that the star is barely radiating at all. The surface temperature is close to the ambient temperature of space. The difference between the star and its surroundings is tiny, and the flow of energy out of the star slows to a trickle. At this stage, the white dwarf is not really cooling in any practical sense. It is asymptotically approaching the temperature of the universe, getting closer and closer but never quite reaching it. The process does not stop, it just becomes so slow that calling it a process feels generous. The challenge of observing white dwarfs becomes extreme once they cool below about 5,000 Kelvin. At that temperature, the star is emitting most of its light in the infrared, and its total luminosity has dropped to a tiny fraction of what it was when it first formed. A white dwarf that started out as bright as the sun might, after 10 billion years of cooling, have a luminosity of 1/10,000th of the sun or less. That is faint, very faint. Detecting an object that dim requires large telescopes with sensitive infrared detectors, and even then, you can only see the ones that are relatively nearby. A cool white dwarf more than a few hundred light-years away is effectively invisible to current technology. It is not that the star is not there, it is that the light reaching us is so faint that it gets lost in the noise. The coolest white dwarfs we have actually observed sit at around 3,000 to 4,000 Kelvin. These are ancient objects, some of them more than 10 billion years old, nearly as old as the universe itself. They are among the faintest stars we can detect. Finding them requires painstaking surveys of the sky, looking for faint infrared sources that move slowly against the background of more distant objects. Once identified, follow-up observations with larger telescopes can measure their spectra, allowing astronomers to determine their surface temperature and composition. From there, cooling models can be used to estimate how long the star has been cooling and, by extension, how old it is. The oldest white dwarfs provide a kind of cosmic clock, a way to measure the age of the galaxy by looking at the oldest stellar remnants still detectable. But even these ancient, faint white dwarfs are nowhere near becoming black dwarfs. They are still warm, they are still radiating, they are still, in a technical sense, alive. The cooling process is only halfway complete, if that. The second half, the long descent from a few thousand Kelvin down to a few Kelvin, will take trillions of years, and by the time that process is finished, the universe will have changed beyond recognition. One of the more sobering aspects of white dwarf cooling is what it implies about the far future of the cosmos. The universe is expanding, and that expansion is accelerating. Galaxies are moving away from each other at an ever-increasing rate, driven by a mysterious force we call dark energy. As the expansion continues, galaxies that are currently visible will eventually recede beyond the cosmic horizon, the point where their light can no longer reach us because the space between us is expanding faster than light can cross it. In a few 100 billion years, every galaxy outside our local group will have disappeared from view. The observable universe will shrink to just the Milky Way, Andromeda, and a handful of smaller satellite galaxies that are gravitationally bound to us. Everything else will be gone, not destroyed, just carried away by the expansion of space. At the same time, stars will continue to burn out. Star formation, the process by which new stars are born from collapsing clouds of gas and dust, will slow and eventually stop as the available gas is used up. The last stars will ignite sometime in the next few trillion years. After that, no new stars will form. The universe will enter what is sometimes called the degenerate era, a period dominated by the slow cooling of stellar remnants. White dwarfs, neutron stars, and black holes will be the only objects left, drifting through the dark, slowly radiating away their energy. The galaxies themselves will dissolve as stars are flung into intergalactic space by gravitational interactions or swallowed by the supermassive black holes at their centers. By the time 10 trillion years have passed, the universe will be a cold, dark, nearly empty place. And the white dwarfs, still cooling, will be among the last objects emitting any energy at all. Even then, they will not be black dwarfs. Not yet. The cooling process will continue, slower than ever, as the temperature difference between the white dwarf and the surrounding universe becomes vanishingly small. The cosmic microwave background, currently at about 3 Kelvin, will have cooled as well, dropping towards zero as the universe expands. The white dwarfs will follow, always lagging slightly behind, always radiating just enough energy to stay warmer than their surroundings by a fraction of a degree. The final approach toward true thermal equilibrium, toward a state where the white dwarf is indistinguishable from the vacuum around it, is not a threshold you cross cleanly. It is an asymptote you crawl toward forever. There is a concept in thermodynamics called heat death, the idea that the universe will eventually reach a state of maximum entropy where no energy is available to do work. In that state, every object in the universe will have cooled to the same temperature. There will be no temperature gradients, no flow of heat, no motion, no change. The universe will be in perfect thermal equilibrium, dead in every sense that matters. Black dwarfs are one of the final signposts on the road to heat death. They represent the end state of stellar evolution, the point at which a star has exhausted every possible source of energy and has nothing left to give. A black dwarf does not shine, it does not radiate, it does not do anything. It is a cold, dark, inert lump of matter sitting in a cold, dark, inert universe. It is the thermodynamic equivalent of a tombstone. The timeline for reaching that state is, again, almost incomprehensibly long. 10 trillion years is the lower estimate. Some models, particularly those that account for exotic physics like proton decay or the slow evaporation of matter through quantum tunneling, push the timeline into ranges that make 10 trillion years look short. If protons are unstable, as some theories of particle physics predict, they will eventually decay into lighter particles over timescales of 10 to the 34th power years or longer. If that happens, white dwarfs will not last as solid objects. They will slowly evaporate, their atoms disintegrating one by one until nothing remains but a diffuse cloud of radiation. In that scenario, black dwarfs, as we define them, solid, cold, stable objects, may never exist at all. But if protons are stable, if matter does not decay, then white dwarfs will persist indefinitely. They will cool, crystallize, and eventually reach thermal equilibrium with the universe. And once they do, they will sit there unchanging for the rest of time. There is no process that can destroy them, no mechanism that can remove them from the universe. They are the ultimate survivors, outlasting stars, galaxies, and possibly even black holes, which are predicted to evaporate over timescales of 10 to the 100th power years through a process called Hawking radiation. By the time the last black hole has evaporated, white dwarfs will still be there, cold and silent, waiting for nothing. The observational challenge posed by cool white dwarfs is not just a matter of brightness, it is also a matter of spectral signatures. Hot white dwarfs emit light across a broad range of wavelengths, making them relatively easy to identify and study. Cool white dwarfs, by contrast, emit almost exclusively in the infrared, and their spectra become increasingly featureless as the temperature drops. The absorption lines that astronomers use to identify elements and measure temperatures become weaker and harder to detect. At very low temperatures, the spectrum is almost a perfect blackbody curve, a smooth, featureless distribution of light that tells you very little beyond the surface temperature. Extracting useful information from such faint, bland spectra requires long exposure times and extremely sensitive instruments. Even then, the data is often noisy and uncertain. One technique astronomers use to find cool white dwarfs is to look for objects with high proper motion, meaning they move noticeably across the sky relative to more distant background stars. White dwarfs are old objects, and old stars tend to have higher velocities because they have had more time to be accelerated by gravitational interactions with other stars and gas clouds. By identifying faint infrared sources that are moving quickly across the sky, astronomers can flag candidates for follow-up observations. This method has been used to discover some of the coolest white dwarfs known, including several that were hiding in plain sight in old survey data, overlooked for decades because they were too faint and too red to stand out. Another method involves looking for white dwarfs in wide binary systems, where the white dwarf orbits a more easily observed companion star. The companion provides a reference point, making it easier to measure the white dwarf's motion and distance. Once the distance is known, the luminosity can be calculated from the observed brightness, and the cooling models can be applied to estimate the age. This technique has been particularly useful for finding old white dwarfs in the solar neighborhood, within a few hundred light-years of Earth, where the observational challenges are slightly less severe. Despite these efforts, the sample of known cool white dwarfs is still small. Astronomers have identified a few dozen candidates with surface temperatures below 4,000 Kelvin and only a handful below 3,500 Kelvin. These are the oldest, coldest white dwarfs currently known, and they are the closest things we have to black dwarfs in the observable universe. They are not black dwarfs, they are still glowing faintly in the infrared. But they are far enough along the cooling curve that they give us a glimpse of what the final stages of stellar evolution look like. They are dim, red, nearly invisible. They are the ghosts of stars that died billions of years ago, and they are still cooling. The concept of thermal death, the point at which a white dwarf stops emitting detectable radiation, is less a hard boundary and more a gradual fade. There is no specific temperature at which a white dwarf officially becomes a black dwarf. Instead, there is a range where the star becomes so cool that its luminosity drops below the threshold of detectability for any conceivable instrument. At that point, the star is effectively a black dwarf, even if it is still technically radiating a tiny amount of energy. The transition is smooth, continuous, and ultimately arbitrary. You cannot point to a specific moment and say, "There, that is when it happened." The star just fades into darkness, one photon at a time, until there is nothing left to see. For practical purposes, astronomers often define a black dwarf as a white dwarf that has cooled to the point where its surface temperature matches the cosmic microwave background. At that point, the star is in thermal equilibrium with the universe. It is not emitting more energy than it is absorbing from the surrounding radiation field. It is, in every meaningful sense, dead. The problem is that reaching that state takes so long that the cosmic microwave background itself will have cooled significantly by the time the first black dwarf forms. The universe is not static. It is expanding and cooling. The background temperature today is about 3 Kelvin. In 1 trillion years, it will be lower. In 10 trillion years, lower still. The white dwarf is chasing a moving target, and the target is moving away faster than the white dwarf can catch up. This creates a strange dynamic where the final cooling stages of a white dwarf are influenced not just by the star's own properties, but by the evolving conditions of the universe around it. A white dwarf cooling in a universe with a 3 Kelvin background will take longer to reach thermal equilibrium than one cooling in a universe with a 1 Kelvin background. The difference is not enormous, but it is real. The universe is, in effect, setting the thermostat, and as the thermostat drops, the cooling process accelerates slightly. Not enough to matter on human timescales, not even enough to matter on cosmological timescales, but over trillions of years, the effect becomes noticeable. The implications of all this for the distant future are stark. In a universe dominated by cooling white dwarfs, there will be no light, No stars, no galaxies, no glow of any kind. The cosmic microwave background will have faded to nearly nothing. The only objects left will be cold, dark remnants drifting through an expanding void. The white dwarfs will be there, invisible, silent, waiting. They will not be doing anything. They will not be evolving. They will just be there, frozen in time, holding on to the last traces of heat from stars that burned out trillions of years earlier, and eventually even that heat will be gone. The white dwarfs will reach thermal equilibrium. They will become true black dwarfs, and the universe will have taken one more step toward its ultimate fate, a state of perfect eternal cold. But before we get to that distant dark future, there is a present to deal with. A present where astronomers are finding some of the coolest, oldest white dwarfs in the galaxy and using them to piece together the history of stellar death. These objects are rare, faint, and difficult to study, but they are out there, scattered through the Milky Way, waiting to be found. They are the oldest survivors, the ones that have been cooling the longest. And they are the closest thing we have to a preview of what the universe will look like trillions of years from now. That is where we turn next. The coldest white dwarf ever found sits about 130 light-years from Earth, barely glowing, radiating so faintly in the infrared that calling it light feels generous. Its catalog name is J0004+1502, though some astronomers just call it L0004+1502 depending on which survey they pulled it from first. Either way, the name is forgettable. What matters is the temperature. 2,500 Kelvin, that is roughly 2,200 degrees Celsius, hot enough to melt steel, hot enough to vaporize most organic compounds instantly. And yet, by white dwarf standards, this object is freezing. It is the coldest stellar remnant we have ever definitively measured, and it is still nowhere close to being a black dwarf. For context, a typical white dwarf, fresh off the production line, has a surface temperature of 20,000 Kelvin or higher. Some start at 50,000, even 100,000 Kelvin if they formed from particularly massive progenitor stars. J0004+1502 has cooled from somewhere in that range all the way down to 2,500 Kelvin. That drop represents roughly 10 billion years of continuous cooling, 10 billion years of slowly radiating energy into space, one photon at a time, with no way to replace what was lost. This white dwarf has been cooling since before the Earth existed. It was already ancient when our solar system was still a cloud of gas and dust circling a newborn sun, and it still has trillions of years to go before it reaches the final stage. The discovery was confirmed in 2023, but the story begins earlier. The European Space Agency's Gaia satellite, launched in 2013, has been quietly mapping the positions, distances, and motions of more than 1 billion stars in the Milky Way. Gaia is not looking for anything specific. It is just measuring everything it can see and building the most detailed three-dimensional map of the galaxy ever attempted. One of the side effects of surveying 1 billion stars is that you inevitably catalog a lot of white dwarfs. Most of them are unremarkable. They sit in the usual temperature range, glowing white or yellow or red, behaving exactly as the models predict. But a small number of objects in the Gaia data stood out as unusually faint and unusually red. Too faint to be normal stars, too red to be typical white dwarfs. These were candidates for something rare, very old, very cool stellar remnants sitting at the edge of detectability. J0004+1502 was one of those candidates. Gaia flagged it as a faint infrared source, moving slowly across the sky relative to more distant background stars. The motion, called proper motion, indicated that the object was relatively nearby, within a few hundred light-years of Earth. That was the first clue. Faint and nearby means intrinsically dim, not just far away, actually dim. From there, the object needed follow-up observations to confirm what it was and how cold it had become. That is where the Very Large Telescope in Chile came in. The VLT is a set of 4 massive optical telescopes perched on a mountain in the Atacama Desert, one of the driest places on Earth. The lack of atmospheric moisture makes it an ideal site for infrared observations, which are easily absorbed by water vapor. The VLT is equipped with an instrument called Hawk-Eye, the high-acuity wide-field K-band imager, designed specifically to detect faint infrared sources. Hawk-Eye pointed at the coordinates flagged by Gaia and started collecting photons. The object was there, glowing dimly in the near-infrared, right where Gaia said it would be. The next step was spectroscopy, splitting the light into its component wavelengths to measure the surface temperature and composition. Spectroscopy at these temperatures is brutally difficult. A white dwarf at 2500 Kelvin emits almost no visible light. The peak of its emission is in the infrared, at wavelengths around 1 to 2 microns. That is just beyond what the human eye can see, but well within the range of instruments like Hawk-Eye. The problem is that the spectrum is almost featureless. At high temperatures, white dwarf spectra are full of absorption lines from hydrogen, helium, and heavier elements in the atmosphere. Those lines act as fingerprints, allowing astronomers to identify the composition and measure the temperature precisely. At low temperatures, those lines weaken and broaden until they almost disappear. What is left is a smooth black body curve, a generic distribution of light that tells you the temperature, but not much else. Extracting a precise measurement from such a bland spectrum requires long exposure times and careful calibration. The team used archival data from the Spitzer Space Telescope, which operated from 2003 until 2020 and specialized in infrared observations, to cross-check the temperature measurement. Spitzer had observed the same region of sky years earlier as part of a different survey, and its data provided an independent confirmation. The surface temperature came out to 2500 Kelvin, give or take 100 degrees. That placed J0004 plus 1502 firmly in the category of ultra-cool white dwarfs, a rare class of objects that have been cooling for most of the age of the universe. The distance measurement provided by Gaia placed the white dwarf at about 130 light-years from Earth. That is relatively close by galactic standards, close enough that the object should have been discovered decades ago if it were any brighter, but it was not brighter. Its absolute luminosity, the total amount of energy it radiates into space, is roughly 1/10,000th that of the Sun. Compare that to a typical white dwarf, which might have a luminosity of 1% of the Sun or higher. J0004 plus 1502 is 100,000 times fainter than a typical white dwarf. It is emitting so little energy that detecting it at all required some of the most sensitive infrared instruments humanity has ever built. The James Webb Space Telescope, which came online in late 2021, has since become the primary tool for studying objects this faint. Webb's Near-Infrared Camera, NIRCam, can detect sources that are orders of magnitude dimmer than what Hubble or Spitzer could see. In 2023, Webb was used to observe a handful of ultra-cool white dwarf candidates identified by Gaia, and the resolution was extraordinary. Objects that appeared as faint smudges in earlier surveys resolved into sharp points of light. Webb's spectroscopic capabilities allowed astronomers to measure temperatures and compositions with unprecedented precision, and in every case where the data was good enough to compare against models, the observations lined up with the predictions. These objects were cooling exactly as the equations said they should. No surprises, no anomalies, just very old, very faint stars slowly ticking toward darkness. One of the more striking aspects of J0004 plus 1502 is how unremarkable it is in every other way. It is not unusually massive. It is not in a binary system. It is not doing anything strange. It is just sitting there, alone, drifting through space, cooling. The star has a mass of about 0.6 times the mass of the Sun, which is typical for white dwarfs. Its radius is roughly the size of Earth, also typical. There are no signs of a companion star, no debris disk, no planets. If there were planets orbiting this star when it was alive, they were either destroyed when the star expanded into a red giant, or they drifted away after the star shed its outer layers. What remains is a solitary object, isolated, forgotten, visible only because we happen to point the right instruments at the right patch of sky at the right time. The cooling timeline for an object like this is sobering. The white dwarf has already been cooling for roughly 10 billion years, more than twice the current age of our solar system. In that time, its surface temperature has dropped from tens of thousands of Kelvin down to 2,500. That is a dramatic drop, but it represents only the first half of the cooling process, maybe less. To cool from 2,500 Kelvin down to 5 Kelvin, the rough threshold where a white dwarf stops emitting detectable radiation and becomes a black dwarf, will take another 10 quadrillion years. That is 10 to the 16th power, a 1 with 16 zeros after it. 10 million billion years. The universe, at 13.8 billion years old, would need to age by a factor of roughly 700,000 before the first black dwarf forms. Put another way, if you compressed the entire history of the universe from the Big Bang to today into a single second, the time required for the Sun's remnant to cool into a black dwarf would be about 8 days. The universe is a newborn. The cooling process has barely started, and objects like J0004 plus 1502, the oldest and coldest white dwarfs we can find, are still in the early stages of a journey that will stretch across timescales so vast that human language struggles to describe them. The observational challenge posed by these ultra-cool white dwarfs is not just about brightness. It is also about what wavelengths you are looking at. A white dwarf at 2,500 Kelvin emits almost exclusively in the infrared. If you pointed a visible light telescope at it, you would see nothing. The object would be invisible, lost against the background of more distant stars and galaxies. To detect it, you need an infrared telescope, and you need one with enough sensitivity to pick out a faint point source against the glow of the sky itself. Infrared observations are difficult because everything warm emits infrared light. The telescope emits infrared. The atmosphere emits infrared. Even the detectors themselves emit infrared as waste heat. Astronomers have to cool their instruments to cryogenic temperatures and use sophisticated techniques to subtract all that background noise before they can see the faint signal from a distant white dwarf. It is a painstaking process, and it only works if the object is relatively nearby. A white dwarf like J0004 plus 1502 would be undetectable if it were more than a few hundred light-years away. The signal would be too weak. It would drown in the noise. This creates a profound observational bias. The cool white dwarfs we have found are almost all in the solar neighborhood, within a few hundred light-years of Earth. That is a tiny fraction of the galaxy, less than 1% of the Milky Way's diameter. There are likely millions of ultra-cool white dwarfs scattered throughout the galaxy, but we can only see the ones that happen to be close enough to detect. The rest are out there, invisible, cooling quietly in the dark. We know they exist because the math says they have to. Stars have been dying and forming white dwarfs for most of the history of the galaxy. The oldest of those white dwarfs, the ones that formed 10 or 12 billion years ago, should have cooled to temperatures of a few thousand Kelvin by now. J0004 plus 1502 is proof that the math is right. The question is, how many more objects like it are out there waiting to be found? One method astronomers use to search for these objects is to look for high proper motion sources in infrared surveys. Proper motion is the apparent movement of a star across the sky over time, measured in arc-seconds per year. Most stars move very slowly, a few milli-arc-seconds per year at most. But nearby stars, especially old ones that have had billions of years to be accelerated by gravitational interactions with other stars and gas clouds, can have much higher proper motions. A white dwarf that is 10 billion years old and only 100 light-years away might move several hundred milliarseconds per year, enough to be noticeable in surveys that compare images taken decades apart. By identifying faint infrared sources with high proper motion, astronomers can flag candidates for follow-up spectroscopy. This technique has been remarkably successful. Many of the coolest white dwarfs known today were discovered by comparing archival survey data and looking for objects that had moved significantly between observations. Another method involves looking for white dwarfs in wide binary systems, where the white dwarf orbits a more easily observed companion star at a large separation. The companion provides a reference point, making it easier to measure the white dwarf's distance and motion. Once the distance is known, the luminosity can be calculated from the observed brightness, and the cooling models can be applied to estimate the age and temperature. This technique has been particularly useful for finding cool white dwarfs in the halo of the Milky Way, the sparse spherical region surrounding the galactic disk where the oldest stars in the galaxy reside. Halo stars are metal-poor, meaning they formed early in the galaxy's history before multiple generations of supernovae had enriched the interstellar medium with heavy elements. The white dwarfs in the halo are correspondingly old, and some of them are among the coolest known. Despite these efforts, the number of confirmed ultra-cool white dwarfs is still small. As of the latest surveys, astronomers have identified fewer than 100 candidates with surface temperatures below 3000 Kelvin and only a handful below 2500 Kelvin. These are the oldest, coldest white dwarfs currently known. They are the survivors, the ones that have been cooling the longest and have somehow remained detectable. They are also the closest things we have to a direct observation of what happens at the tail end of stellar evolution. They are dim, faint, nearly invisible. They are the ghosts of stars that died billions of years ago, and they are still here, still radiating, still refusing to disappear completely. One of the more interesting findings from studying these objects is that their cooling rates match the theoretical predictions almost perfectly. The models developed in the 1960s and refined over the decades since have proven to be remarkably accurate. Astronomers can take the observed temperature and luminosity of a cool white dwarf, plug those numbers into the cooling equations, and calculate how long the star has been cooling. The answer, in almost every case, comes out to somewhere between 8 and 12 billion years, consistent with the age of the galaxy. There are no outliers, no white dwarfs that have cooled too fast or too slow. The process is running exactly as expected, which is both reassuring and slightly unsettling. It means we understand the physics. It also means there are no shortcuts, no tricks, no way to speed up the process or bypass the long, slow march toward darkness. The challenge of confirming a true black dwarf, an object that has cooled all the way to the temperature of the cosmic microwave background and stopped emitting detectable radiation, is insurmountable with current technology. A black dwarf at 5 Kelvin would emit so little energy that no telescope we could conceivably build would be able to detect it. The wavelength of peak emission at 5 Kelvin is in the far infrared, around 600 microns. That is well beyond the range of most infrared detectors, which typically max out at around 30 microns. Even if you had a detector sensitive to those wavelengths, the signal would be absurdly faint. A black dwarf at 100 light-years would have a flux at Earth of roughly 10 to the minus 25 watts per square meter. For comparison, the faintest sources detected by the James Webb Space Telescope have fluxes of around 10 to the minus 18 watts per square meter. A black dwarf would be 10 million times fainter. It would be invisible. The only way to detect a black dwarf would be through its gravitational effects. If a black dwarf passed close to a visible star or a cloud of gas, its gravity would distort the light from the background object, creating a gravitational lensing effect. Or, if a black dwarf were in a binary system with a visible companion, its presence could be inferred from the orbital motion of the companion. These are indirect methods, and they require the black dwarf to be in exactly the right place at the right time. The odds of detecting a black dwarf this way are vanishingly small, and even if you did detect one, you would have no way to measure its temperature or confirm that it had truly reached thermal equilibrium with the universe. You would just know that there was a massive dark object there. Whether it was a black dwarf or something else, a rogue planet, a primordial black hole, would be impossible to say for certain. This is one of the more frustrating aspects of studying the far future of stellar evolution. The final stages, the ones that take trillions of years to play out, are completely inaccessible to direct observation. We can model them, we can simulate them, we can write equations that describe them with extraordinary precision, but we will never see them. The universe is too young, the process is too slow. By the time the first black dwarf forms, humanity, if it still exists in any recognizable form, will have been gone for so long that our entire civilization will be a thin layer of carbon in some distant planetary crust. The stars we see in the night sky will have burned out. The galaxies we observe through telescopes will have receded beyond the cosmic horizon. The universe we know will be unrecognizable, and somewhere in that cold, dark future, a white dwarf will tick over into the final category. It will stop radiating, it will reach thermal equilibrium, it will become a black dwarf, and no one will be there to see it. For now, objects like J0004 plus 1502 are the closest we can get to that distant endpoint. They are the oldest stellar remnants we can still detect, the ones that have cooled the furthest, the ones that give us a glimpse of what the universe will look like trillions of years from now. They are faint, difficult to study, and easy to overlook, but they are also profoundly important. They are the bridge between the theoretical predictions of white dwarf cooling and the observational reality of stellar death. They prove that the models are correct. They show us that the process is real, and they remind us that even the oldest, coldest objects in the universe are still only partway through their journey toward darkness. The question of what happens when that journey finally ends, when the white dwarf cools completely and stops emitting any detectable radiation, is not a question about physics, it is a question about definition. What do you call an object that emits no light, no heat, no radiation of any kind? What do you call a star that is no longer a star in any functional sense? The answer, as we will see, is less straightforward than it sounds, because defining a black dwarf requires deciding where the line is between a very cool white dwarf and something else entirely, and that line, it turns out, is not as clear as you might think. There is a moment in every discussion about stellar evolution when someone has to stop and clarify what is actually being talked about. The terms start piling up: white dwarfs, black holes, brown dwarfs, black dwarfs. They all sound vaguely similar. They all involve the word dwarf or the word black. And somewhere in the back of your mind, you start wondering if astronomers are just making these names up to mess with you. They are not. The names are deliberate, though admittedly not always intuitive. And if you want to understand what a black dwarf actually is, you first need to understand what it is not. Because the confusion surrounding this object is not accidental. It is built into the language, and clearing that confusion up is half the battle. Let's start with the most common point of confusion. A black dwarf is not a black hole. They are not even remotely the same kind of object. The only thing they have in common is the word black, and that word is doing different jobs in each case. A black hole is a region of spacetime where gravity has become so extreme that nothing, not even light, can escape. The defining feature of a black hole is the event horizon, the boundary beyond which the escape velocity exceeds the speed of light. Cross that boundary and you are done. You cannot come back. You cannot send a signal. You cannot do anything except fall toward the singularity at the center, a point where the equations of general relativity break down and the known laws of physics stop making predictions. Black holes are the end result of massive stars collapsing under their own gravity after they exhaust their nuclear fuel. The core collapses, the outer layers either explode or get swallowed, and what remains is a region of space so warped that it tears a hole in the fabric of the universe. That is a black hole, violent, catastrophic, irreversible. A black dwarf is none of those things. A black dwarf does not have an event horizon. It does not have a singularity. It is not a region of warped spacetime. It is an object. A physical, solid object with a surface you could in principle stand on. Not that you should, because the gravity would crush you into a molecular smear, but the point is that there is something there, matter, atoms, a structure you could describe with the same laws of physics that govern everything else. A black dwarf is what happens when a white dwarf, the remnant core of a sun-like star, cools all the way down to the temperature of the surrounding universe and stops emitting any detectable radiation. It is cold, it is dark, it is inert, but it is not a black hole. It has not collapsed into a singularity. It has not punched a hole in space-time. It is just sitting there, held up by electron degeneracy pressure, the same quantum mechanical force that has been holding it up since it first formed billions of years ago. The only thing that has changed is that it has run out of heat. The light has gone out. But the object itself is still there, intact, stable, refusing to collapse any further because quantum mechanics says it cannot. The reason the names sound similar is that both objects are black in the sense that they do not emit visible light. A black hole does not emit light because nothing can escape from inside the event horizon. A black dwarf does not emit light because it has cooled to the point where it no longer has enough thermal energy to radiate. The mechanisms are completely different. The outcomes just happen to look similar from a distance. Both are dark, both are difficult to detect. But one is a hole in the universe. The other is a very cold rock. Those are not the same thing. The second point of confusion involves brown dwarfs. Brown dwarfs are not dead stars. They are failed stars. Objects that never quite made it. They form the same way stars do, from collapsing clouds of gas and dust, but they do not accumulate enough mass to ignite sustained hydrogen fusion in their cores. The cutoff is roughly 75 to 80 times the mass of Jupiter, depending on the composition. Below that threshold, the core temperature never gets high enough to sustain the proton-trayton reaction that powers normal stars. Some brown dwarfs confuse deuterium, a heavier isotope of hydrogen, for a brief period early in their lives, but deuterium is rare and the reaction does not last long. Once the deuterium is exhausted, the brown dwarf just sits there, slowly cooling, radiating away the heat left over from its formation. They glow faintly in the infrared for millions or billions of years, but they are not stars in the traditional sense. They never were. They are substellar objects, a category unto themselves, neither planet nor star, but something in between. A black dwarf, by contrast, is the remnant of a star that succeeded, a star that fused hydrogen into helium for billions of years. A star that, when it ran out of hydrogen, swelled into a red giant and fused helium into carbon and oxygen. A star that shed its outer layers into space and left behind a dense, hot core that has been cooling ever since. A black dwarf is the end state of that process. It is what you get when you take the cooling process all the way to its conclusion. Brown dwarfs are objects that never ignited. Black dwarfs are objects that burned out. The distinction is not subtle. One is a failure to start. The other is a successful completion followed by a very, very long cooldown. The word dwarf in both cases refers to size, but even that is misleading. Brown dwarfs are roughly the size of Jupiter, about 1/10 the radius of the Sun. They are small compared to stars, but they are still enormous by planetary standards. White dwarfs, and by extension black dwarfs, are roughly the size of Earth, much smaller than brown dwarfs. But the term dwarf was applied to white dwarfs first, back in the early 20th century, to distinguish them from red giants and other large stars. The name stuck, and when brown dwarfs were discovered decades later, astronomers kept the theme going. It is not a perfect naming convention. It has caused endless confusion, but it is what we are stuck with, and at this point, trying to rename any of these objects would cause even more problems than it would solve. So what, precisely, is a black dwarf? The formal definition is straightforward. A black dwarf is a white dwarf that has cooled to the point where it no longer emits any significant heat or light. Significant is doing a lot of work in that sentence, so let's be more specific. A black dwarf has reached thermal equilibrium with the cosmic microwave background, the faint afterglow of the Big Bang that fills the universe. That background radiation currently sits at about 3 Kelvin, roughly -270 degrees Celsius. Once a white dwarf cools to that temperature, it stops radiating more energy than it absorbs from the surrounding radiation field. At that point, it is no longer cooling, it is no longer glowing, it is no longer doing anything. It has reached the final stage of its existence. It is a black dwarf. The key word in that definition is significant. Even at 3 Kelvin, an object is not at absolute zero. It still has some thermal energy. Its atoms are still vibrating, albeit incredibly slowly. In principle, it could still emit a photon here and there, a random quantum fluctuation that carries a tiny fraction of energy away. But the rate at which this happens is so low that it is effectively zero. The luminosity of a black dwarf, the total amount of energy it radiates per second, would be so close to zero that no conceivable instrument could detect it. For all practical purposes, the object is dark. It emits no light. It emits no heat. It is thermally dead. The structure of a black dwarf is worth pausing on because it represents the ultimate endpoint of matter under these conditions. The core is fully crystallized. The carbon and oxygen nuclei have locked into a rigid lattice, a single planetary scale crystal held together by electron degeneracy pressure. The outer layers, if any remain, are also solid. There is no liquid, no plasma, no convection. The entire object is a solid block of matter, frozen in place, unmoving. The surface is smooth, featureless. There are no mountains, no valleys, no tectonic activity. Gravity has flattened everything into a near-perfect sphere. The only irregularities would be remnants of whatever magnetic field the white dwarf had when it was still warm, frozen into the lattice as the material cooled and solidified. But even those would be subtle. A black dwarf, if you could somehow see it, would look like a perfectly smooth ball of dark grey rock. No glow, no texture, just a sphere hanging in space, radiating nothing. The mass of a black dwarf is the same as the mass of the white dwarf it used to be. Cooling does not change the mass. A typical black dwarf would weigh roughly half the mass of the Sun, about 1 × 10⁻30th power kilograms, compressed into a sphere the size of Earth. The density is staggering. A sugar cube of black dwarf material would weigh about a ton. A teaspoon would weigh as much as an elephant. And yet, despite that density, the object is stable. It is not collapsing. It is not contracting. It is held up by electron degeneracy pressure, the same force that has been supporting it since it first became a white dwarf billions of years ago. That pressure is not going away. It is a consequence of quantum mechanics, and quantum mechanics does not change just because the object has cooled. The electrons are still packed into the lowest available energy states, still obeying the Pauli exclusion principle, still refusing to be compressed any further. The black dwarf is not collapsing because it cannot collapse. The universe will not let it. There is a subtlety here that is easy to miss. A black dwarf is not at absolute zero. It is at the temperature of the cosmic microwave background, which is currently about 3 Kelvin and dropping. The universe is expanding, and as it expands, the cosmic microwave background cools. In the far future, trillions of years from now, the background temperature will be lower than it is today. Eventually, it will approach zero. But it will never reach zero, not in any finite amount of time. Absolute zero is a mathematical limit, not a physical state you can actually achieve. There is always some residual energy left over, some tiny vibration or fluctuation that refuses to disappear completely. A black dwarf, therefore, is never truly at absolute zero. It is just close enough that the difference does not matter for any practical purpose. This creates an interesting philosophical question. If a black dwarf is not quite at absolute zero, is it still radiating? Technically, yes. Any object with a temperature above absolute zero emits some amount of thermal radiation, no matter how faint, but the rate at which a black dwarf radiates is so low that it is effectively undetectable. The power radiated by an object is proportional to the 4th power of its temperature. At 3 Kelvin, a black dwarf would radiate roughly 10 to the minus 30 watts per square meter. For comparison, a typical incandescent light bulb emits about 60 watts. A black dwarf the size of Earth would emit less energy in a year than a light bulb emits in a fraction of a second. That is not zero. But it is close enough that calling it dark is not an exaggeration. The question of whether black dwarfs actually exist is simpler than it sounds. They do not yet. The universe is too young. The cooling process takes too long. The oldest white dwarfs in the universe, the ones that formed 10 or 12 billion years ago, are still glowing faintly in the infrared. They are still warm. They are still radiating energy at a rate high enough to be detected with sensitive telescopes. The coolest white dwarf we have ever found has a surface temperature of about 2,500 Kelvin. That is cold by white dwarf standards, but it is still hot by any reasonable definition. It is nowhere close to 3 Kelvin. The timeline for cooling from 2,500 Kelvin down to 3 Kelvin is roughly 10 quadrillion years. That is 10 to the 16th power, a 1 with 16 zeros after it. The universe would need to age by a factor of about 700,000 before the first black dwarf forms. We are not even close. This is one of the stranger aspects of astrophysics. We have an entire category of object, a formal definition, a name, a set of predicted properties, and not a single example. Black dwarfs are purely theoretical. They are the inevitable conclusion of a process we understand in great detail, but they do not exist yet. They will exist. The math says they must, but they are not here now. They are waiting in a future so distant that the word future stops making intuitive sense. And yet, astronomers talk about them as if they were real. They write papers about their properties. They model their formation. They debate what they will look like and how they will behave, all for an object that has never been observed and will not exist for trillions of years. It is one of the few cases in science where the theory is so solid, so well established, that the lack of direct evidence does not matter. We know black dwarfs will exist because we know how white dwarfs cool. The process is deterministic. There are no surprises left. Just time. The distinction between a very cool white dwarf and a black dwarf is not a hard boundary. It is a gradual transition. There is no specific temperature at which you can point to a white dwarf and say, "There, that is when it became a black dwarf." The star just fades into darkness, one photon at a time, until its luminosity drops below the threshold of detectability. At that point, it is effectively a black dwarf, even if it is still technically radiating a tiny amount of energy. The transition is smooth, continuous, and ultimately arbitrary. You cannot observe it, you cannot measure it. You can only calculate when it should happen and accept that by the time it does, no one will be around to confirm it. The properties of a black dwarf are defined entirely by what it is not. It is not hot. It is not glowing. It is not fusing anything. It is not collapsing. It is not evaporating. It is not doing anything. It is a remnant, a fossil, a leftover piece of a process that ended billions of years ago. The only reason we care about black dwarfs is that they represent the final stage of stellar evolution for the vast majority of stars in the universe. Every star between about 0.8 and 8 solar masses will eventually become a white dwarf, and every white dwarf will, given enough time, become a black dwarf. That means black dwarfs are not rare. They are not exotic. They are the default outcome for most stars. They are what the universe looks like in the far future, once all the burning has stopped and all the light has faded. They are the tombstones of stellar evolution, silent, dark, eternal. The fact that black dwarfs do not have singularities is worth emphasizing because it distinguishes them fundamentally from black holes. A singularity is a point where the laws of physics break down, where density becomes infinite and space-time curvature becomes infinite, and the equations stop giving meaningful answers. Black holes have singularities at their centers. Black dwarfs do not. The matter inside a black dwarf is dense, extraordinarily dense, but it is not infinitely dense. It is governed by the equations of quantum mechanics and thermodynamics. It obeys the same rules as ordinary matter, just under extreme conditions. There is no point inside a black dwarf where the laws of physics fail. The entire structure, from the surface to the core, is describable using the same framework we use to describe everything else. That makes black dwarfs fundamentally different from black holes, which are singularities wrapped in event horizons, objects that exist at the edge of what physics can explain. The ultimate fate of a black dwarf depends on assumptions about the stability of matter. If protons are stable, as most evidence suggests, then black dwarfs will persist indefinitely. They will sit in space, unchanging for the rest of time. There is no process that can destroy them, no mechanism that can remove them from the universe. They are the final form of stellar matter, locked in place by quantum mechanics, waiting for nothing. But if protons are unstable, as some grand unified theories predict, then black dwarfs will not last forever. Protons are predicted to decay over timescales of 10 to the 34th power years or longer, depending on the theory. If that happens, the matter inside a black dwarf will slowly disintegrate, one proton at a time, until nothing remains but a diffuse cloud of lighter particles and radiation. In that scenario, black dwarfs are only temporary. They are a waypoint, not an endpoint. They exist for an incomprehensibly long time, but they do not exist forever. The universe, given enough time, will erase them completely. For now, though, the question of proton decay is unresolved. Experiments have searched for it and found nothing. The current lower limit on the proton lifetime is about 10 to the 34th power years, meaning that if protons decay at all, they do so on timescales far longer than the current age of the universe. That is long enough that, for practical purposes, you can assume protons are stable and black dwarfs will last indefinitely. But the uncertainty remains, and it is one of the few open questions left in the story of white dwarf cooling. Either black dwarfs are the final resting state of stellar matter, or they are a temporary phase that will eventually evaporate into nothing. We do not know which. We might never know. The timescales involved are so vast that confirming proton decay experimentally is nearly impossible. You would need to watch a large sample of protons for longer than the universe has existed to see even one decay. That is not a feasible experiment. The concept of a black dwarf as the heat death of a sun-like star is not metaphorical, it is literal. Heat death is the term physicists use to describe a state where no energy is available to do work. In thermodynamic terms, it means maximum entropy. Everything has reached the same temperature. There are no temperature gradients, no flow of heat, no motion, no change. The system is dead. A black dwarf is a localized example of heat death. It has exhausted all its available energy. It has radiated everything it had. It is in thermal equilibrium with the universe. It cannot do anything because there is no energy left to do it with. It is the end of the line. And yet, there is a twist, a final, unexpected chapter in the life of a black dwarf that was only predicted in the last few decades. It turns out that even in the far future, even after the universe has gone cold and dark, even after every star has burned out and every galaxy has dissolved, there is still one more way for a black dwarf to go out, not with a whimper, with a bang. A massive, galaxy-illuminating explosion that will, for a brief moment, be the only light in an otherwise empty universe. That explosion, that final spark, is where the story of black dwarfs takes its strangest turn, and it is where we go next. There is an explosion coming, not soon, not in any time frame that makes sense to talk about using the word soon, but coming nonetheless, an explosion so distant in the future that by the time it happens the universe will have been cold and dark for longer than stars existed in the first place. An explosion that will for a brief moment be the only light in a cosmos that has forgotten what light is. And the object producing that explosion will be a black dwarf. A stellar corpse that has been dead for trillions upon trillions of years, sitting in the dark doing nothing, until one day, without warning, it tears itself apart in a blast bright enough to outshine entire galaxies that no longer exist. This is not science fiction. This is the inevitable conclusion of a process that starts the moment a white dwarf begins to cool. And the truly strange part is that we only figured this out in the last few years. The theory of black dwarf supernovae was not proposed until 2020, published by a physicist named Matt Kaplan at Illinois State University. Before that, astronomers assumed black dwarfs were the end of the line, inert, stable, eternal. Kaplan looked at the same physics everyone else was looking at and realized they had missed something. Black dwarfs are not done. They are waiting, and what they are waiting for is one of the most bizarre nuclear processes the universe can produce. The setup is straightforward. You take a white dwarf. You let it cool for 10 trillion years until it becomes a black dwarf. You wait a long time, longer than any other process we have ever described. And then, if the conditions are exactly right, the carbon and oxygen nuclei locked in the crystalline core begin to fuse, not because the star is hot, it is cold, colder than anything in the universe today. The fusion happens anyway, driven by a purely quantum mechanical process called tunneling. The nuclei, sitting in their fixed lattice positions, vibrating almost imperceptibly, occasionally quantum tunnel through the electrostatic barrier that normally keeps them apart. When that happens, they fuse. Carbon fuses with carbon, oxygen fuses with oxygen. The products are heavier elements, neon, magnesium, silicon, and eventually, after enough tunneling events have stacked up, the core starts producing nickel-56. That is where the trouble begins. Nickel-56 is radioactive. It decays rapidly on a time scale of days into cobalt-56, which then decays into iron-56. Each decay releases energy in the form of gamma rays. In a normal supernova, this is what powers the light curve, the gradual fade of the explosion over weeks and months as the nickel decays and the energy escapes into space. In a black dwarf, the nickel is being produced deep inside a cold, solid, crystalline core. The gamma rays cannot escape. They are trapped, absorbed by the surrounding material, heating it. And heating a white dwarf, even slightly, weakens the electron degeneracy pressure holding it up. The core contracts. The contraction increases the density. The increased density accelerates the tunneling rate. More fusion, more nickel, more heating, more contraction. The process feeds on itself, a runaway reaction that happens faster and faster until the entire core undergoes explosive nuclear burning in a matter of seconds. The black dwarf detonates. The explosion rips through the star, unbinding it completely. What was a cold, dark, inert sphere the size of Earth becomes a rapidly expanding cloud of plasma, iron, and radiation. A supernova. In a universe that has not seen a supernova for longer than it takes to count to infinity. The timeline for this to happen is the part that makes your brain shut down. The first black dwarf supernova is predicted to occur in about 10 to the 1100th power years. That is a 1 followed by 1100 zeros, not 1100 years, 1100 zeros. Writing that number out in full would take multiple pages. Saying it out loud is meaningless. The human brain has no framework for processing a number that large. For comparison, the current age of the universe is about 10 to the 10th power years. That is a 1 with 10 zeros, 13.8 billion. The time until the first black dwarf supernova is 10 to the 1100th power. If you took the current age of the universe and multiplied it by itself 100 times, you would still be nowhere close. The gap between now and the first black dwarf supernova is wider than the gap between the Big Bang and now by a factor so large that there is no word for it in any human language, and that is just the first one. The last black dwarf supernova is predicted to occur around 10 to the 32,000th power years. 10 to the 32,000, a 1 followed by 32,000 zeros. At that point, the timeline has become so absurd that even physicists stop trying to make sense of it. You cannot visualize it. You cannot compare it to anything. You can only write the equation and accept that the math says it is real. By the time the last black dwarf supernova goes off, The universe will have been in a state of heat death for so long that the entire era of stars, galaxies, and structure will look like a brief flicker at the very beginning of time. Everything we think of as the universe, everything we observe, everything we measure, will have occupied the first infinitesimal fraction of cosmic history. The rest will be cold, dark, empty, and silent. Except for these explosions, rare, scattered across unimaginable gulfs of time and space, brief sparks in an otherwise lightless void. The mechanism driving this process is called pycnonuclear fusion. The term comes from the Greek word pyknos, meaning dense. Pycnonuclear fusion is fusion that occurs in matter so dense that the nuclei are close enough for quantum tunneling to become statistically significant. In a normal star, fusion happens because the temperature is high enough that nuclei collide with enough kinetic energy to overcome the electrostatic repulsion between them. Two protons, both positively charged, repel each other. To fuse them, you need to smash them together hard enough that the strong nuclear force, which operates at very short ranges, can take over and bind them into a heavier nucleus. That requires temperatures of millions of degrees. Pycnonuclear fusion works differently. The nuclei are not moving fast. They are sitting in a solid lattice, vibrating slightly but mostly stationary. The temperature is close to zero. There is no kinetic energy to speak of, and yet occasionally a nucleus will quantum tunnel through the electrostatic barrier and fuse with a neighboring nucleus. Tunneling is a purely quantum phenomenon. It allows particles to pass through energy barriers that classical physics says they should not be able to cross. It is the same process that allows alpha particles to escape from radioactive nuclei during alpha decay. The particle does not have enough energy to climb over the barrier. It just appears on the other side, as if the barrier were not there. Quantum mechanics allows this. The probability is low, but it is not zero, and given enough time, low probability events become certainties. In a black dwarf, the nuclei are packed so closely together that the distance they need to tunnel is short. The probability of tunneling is still incredibly low. A single nucleus might sit in its lattice position for 10 to the 100th power years before it tunnels into a neighboring nucleus and fuses, but a black dwarf contains something like 10 to the 57th power nuclei. That is a lot of opportunities. And when you multiply a very small probability by a very large number of attempts over a very long period of time, you start getting fusion events. Not many, not fast, but enough. Over trillions upon trillions of years, the fusion events accumulate. Carbon fuses with carbon to produce magnesium. Oxygen fuses with oxygen to produce silicon. The products of those reactions can themselves fuse with other nuclei, climbing up the periodic table one step at a time. Eventually, after an unimaginable number of tunneling events, the core starts producing iron. Iron is the most stable nucleus. It has the lowest energy per nucleon of any element. Fusing iron costs energy instead of releasing it, so once the core fills with iron, fusion stops. The star becomes an iron black dwarf, a cold sphere of iron nuclei held together by electron degeneracy pressure. That is the endpoint. Iron black dwarfs do not explode. They just sit there forever, inert, stable, eternal. But not all black dwarfs make it to that stage. Some explode before the iron core has fully formed. These are the ones that produce black dwarf supernovae. The critical factor is mass. A black dwarf needs to be close to the Chandrasekhar limit, about 1.4 solar masses, for the pycnonuclear fusion to trigger a runaway explosion. Below that mass, the fusion produces nickel, but not enough to destabilize the star. The nickel decays, the energy dissipates, and the star keeps cooling. Above the Chandrasekhar limit, the star is already unstable. It will collapse into a neutron star or black hole long before it has a chance to cool into a black dwarf. The sweet spot is right at the limit, where the electron degeneracy pressure is barely strong enough to hold the star up. In that configuration, even a small amount of heating from nickel decay is enough to tip the balance. The core contracts, the density increases, the tunneling rate accelerates, and the star explodes. The fraction of black dwarfs that will actually explode is small. Kaplan's models suggest that only about 1% of all black dwarfs will be massive enough and will accumulate enough nickel to trigger a supernova. The rest will cool peacefully, fuse their cores into iron over timescales even longer than the supernova timeline, and sit there forever. But 1% of all white dwarfs is still a lot of explosions. There are billions of white dwarfs in our galaxy alone. If 1% of them eventually explode as black dwarf supernovae, that means billions of explosions scattered across a timeline so vast that the words billions and timeline stop meaning anything. Each explosion will be brief. A few weeks of brightness, followed by a slow fade. But in a universe that has been dark for 10 to the 1000th power years, even a few weeks of light is an event. It is the only event. There is nothing else happening. No stars are burning, no galaxies are colliding, no black holes are accreting. The universe is static, cold, dead. And then, somewhere in the void, a black dwarf detonates. For a brief moment there is light, then darkness again, and the wait begins for the next one. The energy released in a black dwarf supernova is comparable to a Type 1a supernova, the kind that occurs when a white dwarf in a binary system accretes enough material from a companion star to push it over the Chandrasekhar limit and trigger a thermonuclear explosion. Type 1a supernovae are among the brightest events in the universe, briefly outshining entire galaxies. A black dwarf supernova would release a similar amount of energy, roughly 10 to the 44th power joules, enough to unbind the entire star and eject its mass into space at thousands of kilometers per second. The explosion would produce a rapidly expanding shell of hot plasma, rich in iron and other heavy elements. In the current universe, such an explosion would seed the surrounding interstellar medium with material for future generations of stars and planets. In the universe of black dwarf supernovae, there is no interstellar medium. There are no future generations. The ejector expands into a vacuum, cooling as it goes, eventually dispersing into a thin cloud of atoms that will drift through space forever, alone. The observational signature of a black dwarf supernova would be unmistakable if anyone were around to observe it. The spectrum would show strong lines of iron, nickel, and other iron peak elements, the same signatures seen in Type 1a supernovae today. The light curve would follow the same pattern, a rapid rise to peak brightness, followed by an exponential decay as the nickel-56 decays into cobalt and then iron. The peak luminosity would be enormous, bright enough to be visible across vast distances, even in a universe where space has expanded so much that the concept of distance has lost most of its meaning, but there is no one to see it. By the time the first black dwarf supernova occurs, humanity will have been gone for so long that our entire species, our entire civilization, every thought we ever had and every structure we ever built, will have been reduced to atoms scattered across a cold, empty cosmos. The Earth will have been consumed by the Sun during its red giant phase, an event that will happen in about 5 billion years. The Sun itself will have cooled into a black dwarf trillions of years after that. And then, quadrillions of years later, if the Sun's remnant is massive enough and lucky enough, it will explode, and no one will see it. There will be no telescopes, no observers, no one left to care. The question of whether black dwarf supernovae will actually happen depends on one major assumption: protons have to be stable. If protons decay as some grand unified theories predict, then black dwarfs will not last long enough to explode. Proton decay is predicted to occur on timescales of 10 to the 34th power years or longer, depending on the theory. If that happens, the matter inside a black dwarf will slowly disintegrate, one proton at a time, until the entire object evaporates into a diffuse cloud of lighter particles and radiation. The black dwarf will be gone long before pycnonuclear fusion has a chance to build up enough nickel to trigger an explosion. In that scenario, black dwarf supernovae do not happen. The universe skips straight to heat death, and there are no final sparks, just silence. But if protons are stable, and current experimental evidence suggests they are, then black dwarf supernovae are inevitable. The math is clear. The tunneling rates are well understood. The process is deterministic. Given enough time, the carbon and oxygen in a black dwarf's core will fuse, the nickel will accumulate, the heating will destabilize the core, and the star will explode. The timeline is absurd. The wait is unimaginable, but the outcome is certain. These explosions will happen. They will be the last energetic events the universe can produce, the final supernovae, the last light before the final darkness. There is something deeply poetic about the idea that the universe's last act, its final dying gasp, will be the explosion of a star that has been dead for trillions of years. A star that cooled, crystallized, and sat in the dark for longer than stars existed in the first place, only to suddenly, violently tear itself apart in a blaze of gamma rays and iron. It is a reminder that even in a universe heading inexorably toward heat death, toward a state of maximum entropy where nothing can ever happen again, there are still surprises waiting. Still processes playing out on timescales so long that even the concept of time becomes strained. The universe is not done. It will not be done for 10 to the 32,000th power years, and maybe not even then. There are mechanisms still ticking, reactions still proceeding, events still scheduled to occur in a future so distant that the word future loses all meaning, and black dwarf supernovae are one of them. The strangest part is that we figured this out at all. Matt Kaplan sat down with the equations for quantum tunneling, the known cooling rates for white dwarfs, the density profiles of crystalline cores, and the nuclear reaction rates for carbon and oxygen fusion, and he worked out what happens if you let the process run for long enough. The answer, it turns out, is that the star explodes. No one had bothered to check before. Why would they? The timescales are so absurd that they feel irrelevant. Who cares what happens in 10 to the 1000th power years? The universe will be unrecognizable by then. Humanity will be gone. The stars will be gone. The galaxies will be gone. Why does it matter? Kaplan's answer is simple. It matters because it is true. The physics says it will happen. And if the physics says it will happen, then it will happen, whether anyone is around to see it or not. The universe does not care if we are watching. It just keeps running the equations. The practical implications of black dwarf supernovae are, to put it mildly, non-existent. There is no scenario in which humanity or any conceivable civilization survives long enough to witness one. The timescales are too long. The universe will have changed too much. By the time the first black dwarf supernova occurs, the very concept of civilization, of life, of structure, will have been irrelevant for longer than it was relevant. These explosions are not a threat. They are not an opportunity. They are just a fact, a prediction, a data point on the timeline of cosmic evolution that extends so far into the future that it might as well be infinity. But infinity, it turns out, is not infinite. It is just very, very large, and even very large numbers eventually end. There is one more wrinkle. The timeline for black dwarf supernovae assumes that the universe continues to expand at its current rate, or faster, driven by dark energy. If dark energy behaves the way current models suggest, then the expansion will accelerate, the cosmic microwave background will continue to cool, and the universe will asymptotically approach a state of maximum entropy over timescales of 10 to the 120th power years or longer. In that scenario, black dwarf supernovae are real events that will actually happen. But if dark energy changes, if the expansion slows or reverses, if the universe eventually collapses in a big crunch, then the timeline changes. A collapsing universe heats up. The cosmic microwave background gets hotter, not cooler. Black dwarfs stop cooling and start warming. They never reach the cold, stable state required for pycnonuclear fusion to dominate. The supernovae do not happen. The universe ends in fire, not ice. We do not know which scenario is correct. Current observations favor continued expansion, but the uncertainties are large. Dark energy is poorly understood. Its equation of state, the relationship between its pressure and density, is constrained by observations but not definitively measured. A small change in that equation could change the fate of the universe completely. For now, the best guess is that the universe will expand forever, cool forever, and eventually reach a state where black dwarf supernovae are the only events left. But it is a guess, an informed guess, backed by data, but still a guess. The fact that black dwarf supernovae might be the last supernovae raises an interesting philosophical question. What is the point of an explosion that no one will ever see? A supernova is, in some sense, a message. It is the death of a star, announced to the universe in a burst of light and energy that can be detected across billions of light years. It seeds the cosmos with heavy elements. It triggers star formation in nearby gas clouds. It leaves behind a remnant, a neutron star or black hole that continues to interact with its environment for millions of years. A supernova matters because it affects other things. It is part of a larger story. But a black dwarf supernova happens in a universe that is empty. There are no nearby gas clouds. There is no star formation. There are no observers. The explosion occurs. The light spreads outward, and then it fades. The ejector expands into a void. The heavy elements drift through space, alone, cooling, until they too reach thermal equilibrium with the universe. The explosion changes nothing. It has no consequences. It is an event that happens and then stops, with no lasting impact on anything. In a universe that has reached heat death, events do not matter because there is nothing for them to matter to. The black dwarf supernova is the ultimate pointless act. A spectacular, violent, energetic explosion that happens for no reason and accomplishes nothing, and yet it happens because the physics says it must. Maybe that is the real lesson here. The universe does not care about meaning. It does not care about purpose. It does not care if anyone is watching or if anything matters. It just runs the equations. It takes the rules, the laws of thermodynamics and quantum mechanics and general relativity, and it applies them consistently, relentlessly, forever. And sometimes those rules produce black dwarf supernovae, explosions in the dark, light where there should be none, a final spark in a universe that has forgotten what fire is. Not because the universe is trying to tell us something, not because there is some grand plan or cosmic significance, just because the math works out that way. And in the end, maybe that is enough. The future the universe is heading toward is not a future we can participate in. It is not even a future we can meaningfully imagine. It is a timeline so long, a state so cold and empty, that the very concepts we use to think about existence stop applying. And yet, somewhere in that distant, incomprehensible future, there will be light, brief, rare, pointless, but light nonetheless. The last supernovae, the final sparks, the universe's way of saying that even after everything has ended, even after heat death has claimed every star and every galaxy and every trace of structure, the show is not quite over. There is still one more act, one more explosion, one more burst of energy before the final, eternal silence. And that, perhaps, is the strangest and most beautiful part of the story. That even at the end of everything, the universe still has surprises left. The last lights go out, sometime around 10 to the 15th power years. Not all at once, not with any ceremony, just a slow, patient fade as the final white dwarfs cool past the point where they can emit anything you could call light. By that point, the universe has been expanding for 1,000 times longer than it has existed today. The cosmic microwave background, the faint afterglow of the Big Bang, has cooled to a fraction of a degree above absolute zero. The galaxies, or what used to be galaxies, have long since dissolved. Their stars were flung into intergalactic space by gravitational interactions or swallowed by the supermassive black holes at their centers. Those black holes are still there, but they are not feeding. There is nothing left to feed on. They sit in the dark, slowly evaporating through Hawking radiation, a process so glacial that it makes white dwarf cooling look frantic. And scattered through this void, drifting alone through space so empty that calling it space feels generous, are the black dwarfs. Trillions of them, billions of trillions. Cold, dark, silent spheres the size of planets, each one the fossilized core of a star that burned out so long ago that the light from its death has traveled to the edge of the observable universe and back 1,000,000 times over. This is the black dwarf era, the degenerate era, the age when the universe is dominated not by stars or galaxies or any kind of active process, but by remnants, objects that are no longer doing anything. No fusion, no radiation, no motion beyond the slow drift through expanding space. The black dwarfs are not alive in any sense that matters. They are not evolving. They are not interacting with anything. They are just there, held together by electron degeneracy pressure, the same quantum mechanical force that has been holding them up since they first formed tens of trillions of years earlier. And they will stay there, unchanging, for the rest of time, or at least until the universe finds one more way to surprise us. The transition into this era is not abrupt. There is no moment where you can point to the universe and say, there, that is when the black dwarf era began. It is a gradual shift that happens over trillions of years as the last stars burn out and the last white dwarfs cool below the threshold of detectability. The timeline depends on the type of star you are talking about. Massive stars, the ones that end their lives in supernovae, are already gone. They burned bright and fast, exhausting their fuel in a few million years, and they have been neutron stars or black holes for tens of billions of years by the time the black dwarf era even begins. Sun-like stars, the ones that become white dwarfs, take longer. They can burn for 10 billion years or more before they run out of hydrogen and start the process of dying. And the smallest stars, the red dwarfs, the dim, cool, long-lived stars that make up the majority of the stellar population, can burn for trillions of years. These are the last stars left, the final holdouts. By the time they finally exhaust their fuel and fade into darkness, the universe is already 100 trillion years old. 100 trillion. That is 7,000 times longer than the universe has existed today, and at that point, the last light goes out. The last fusion reaction sputters to a stop. The last photon from the last dying star stretches into the infrared and fades, and the universe enters a phase where nothing is burning, nothing is glowing, nothing is happening, except the black dwarfs. They are still there. They have been there the whole time, accumulating as stars died and cooled and crossed the threshold from white dwarf to black dwarf. By the time the last red dwarf goes dark, the black dwarf population has been growing for tens of trillions of years, and it will keep growing technically as the remaining white dwarfs continue to cool and join the club. But at this point, the distinction between a very cool white dwarf and a black dwarf is academic. The universe is so cold that the difference does not matter. Everything is dark. Everything is inert. The black dwarf era is not an event. It is a state, a configuration of the universe where the dominant form of matter is cold, degenerate stellar remnants drifting through an ever-expanding void. The scale of this era is difficult to overstate. It lasts from roughly 10 to the 30th power years until about 10 to the 40th power years. That is a span of time so long that the entire history of stars, from the first ones that lit up a few 100 million years after the Big Bang, to the last red dwarfs that finally burned out 100 trillion years later, occupies less than 1/1,000,000th of 1% of it. Put another way, if you took the age of stars and stretched it across the width of a human hair, the black dwarf era would circle the Earth 1 billion times. Stars, the objects we think of as the defining feature of the universe, the things we build telescopes to look at and write equations to understand, are a brief flicker at the very beginning of cosmic history. The rest is cold, dark remnants. The rest is silence. There is something profoundly unsettling about this. We live in a universe that is, by any reasonable measure, full of activity. Stars are fusing, galaxies are colliding, black holes are accreting, planets are orbiting. Life, at least on this one planet we know about, is thriving. The universe feels alive, dynamic, full of process and change and motion. And it is easy to assume that this is just how the universe is, that this is the default state. But it is not. The universe we live in is a temporary condition, a brief era of star formation and galactic structure that began about 13.8 billion years ago and will end in a few trillion years. After that, the universe transitions into something else, something colder, something quieter, something where the defining feature is not the presence of activity but the absence of it. The black dwarf era is not an anomaly. It is not a side note in the history of the cosmos. It is the main event. It is what the universe looks like for most of its existence, and we are just not around to see it. The physics of the black dwarf era is straightforward. The universe is expanding, driven by dark energy, a mysterious force that pushes space itself apart at an accelerating rate. As the universe expands, the distance between objects grows. Galaxies that are currently billions of light years apart will eventually be trillions of light years apart. Then quadrillions. The expansion does not stop. It does not slow down. It accelerates. And as it accelerates, the cosmic microwave background, the faint glow of the Big Bang, continues to cool. The temperature drops from the current 3 Kelvin down to 1 Kelvin, then 1/10 of a Kelvin, then 100th, asymptotically approaching zero but never quite getting there. At the same time, the black dwarfs are cooling. They are radiating away the last traces of thermal energy they have left, one photon at a time, until their temperature matches the background. At that point, they stop cooling, not because they have reached absolute zero, but because they are in thermal equilibrium with the universe. They are no longer warmer than their surroundings. They are just part of the background, indistinguishable from the void around them, except for the fact that they have mass and the void does not. The distribution of black dwarfs in this future universe is worth thinking about because it highlights just how empty space has become. Today, the average density of the universe is about 5 atoms per cubic meter. That is already incredibly sparse. A vacuum pump in a laboratory can create a much better vacuum than the average density of space. But in the black dwarf era, the density is lower, much lower. The expansion of the universe has stretched space so much that the distance between objects has grown by factors of billions or trillions. A black dwarf that is currently 100 light-years from its nearest neighbor might be 1,000,000 light-years away by the time the black dwarf era is in full swing. And the trend continues. The farther into the future you go, the more isolated each black dwarf becomes. They are not in clusters. They are not in groups. They are alone, drifting through a space so vast and so empty that the word empty stops being adequate. Each black dwarf is its own island, its own isolated system. There is no interaction, no gravitational influence from neighboring objects, no light from distant sources, just a sphere of cold matter sitting in an infinite void, doing nothing. The concept of entropy ties into all of this in a way that is both elegant and depressing. Entropy is a measure of disorder, or more precisely, a measure of how much energy in a system is unavailable to do work. In a low entropy state, energy is concentrated and organized. You have hot things and cold things, and the difference in temperature allows energy to flow from one to the other. That flow can do work. It can power a steam engine, it can drive chemical reactions, it can sustain life. In a high entropy state, everything is at the same temperature. There are no gradients, no flow, no work. The system is in equilibrium. And equilibrium, in thermodynamic terms, is another word for death. The universe started in a very low entropy state. The Big Bang was an incredibly hot, dense, organized event. Energy was concentrated. Structure was minimal. And then the universe expanded. As it expanded, it cooled. As it cooled, structure formed. Galaxies, stars, planets, life. All of this is a local decrease in entropy, made possible by the fact that the universe as a whole is still far from equilibrium. The sun can shine because it is hot and space is cold. The energy flows outward, and that flow powers everything on Earth. But the overall trend is toward higher entropy. The universe is moving inexorably toward a state where everything is the same temperature and no energy flow is possible. Physicists call this heat death, and the black dwarf era is what heat death looks like. By the time the universe reaches the black dwarf era, entropy has increased to the point where almost no useful energy remains. The stars have burned out. The black holes are evaporating. The cosmic microwave background has cooled to near zero. The black dwarfs are in thermal equilibrium with their surroundings. There is nowhere for energy to flow. No temperature gradients, no motion. The universe has reached, or is very close to reaching, maximum entropy. And in that state, nothing can happen. Not because the laws of physics have changed, but because there is no available energy to drive any process. The second law of thermodynamics, which says that entropy always increases in a closed system, has run its course. The universe has wound down, and what is left is a cold, dark, silent expanse of space dotted with cold, dark, silent remnants that will persist unchanged for the rest of time. There is a counter-argument, or at least a complication, that involves the possibility of proton decay. Protons, the positively charged particles in atomic nuclei, are generally assumed to be stable. We have never observed one decay. Experiments designed to detect proton decay have placed a lower limit on the proton lifetime of about 10 to the 34th power years. That is an enormously long time, much longer than the current age of the universe. But some theories of particle physics, particularly grand unified theories that attempt to merge the electromagnetic, weak and strong nuclear forces into a single framework, predict that protons are not truly stable. They predict that protons will, given enough time, decay into lighter particles. A proton might decay into a positron and a neutral pion, for example, which would then decay further into photons and other particles. If this happens, it changes the story of the black dwarf era dramatically. If protons decay, black dwarfs do not last forever. The matter inside them, the carbon and oxygen nuclei locked in a crystalline lattice, will slowly disintegrate, one proton at a time, over timescales of 10 to the 34th power years or longer. The nuclei will break apart. The black dwarf will lose mass. Its structure will weaken. Eventually, after an incomprehensible span of time, the entire object will evaporate into a diffuse cloud of lighter particles and radiation. At that point, there are no more black dwarfs, no more solid objects at all. Just a thin soup of particles drifting through space, slowly thermalizing with the expanding universe. In this scenario, the black dwarf era is not the final state of matter. It is a temporary phase lasting for trillions upon trillions of years, but not forever. The ultimate fate of matter is to dissolve completely, leaving behind nothing but radiation and space. But if protons are stable, and the evidence so far suggests they are, then black dwarfs persist indefinitely. They do not evaporate. They do not decay, they just sit there inert, held together by electron degeneracy pressure, waiting for nothing. In this scenario, the black dwarf era is not a temporary phase. It is the final configuration of the universe, the endpoint. And the timeline stretches not just to 10 to the 40th power years, but beyond, to 10 to the 100th power years, to 10 to the 1000th power years, to infinity, assuming infinity has any meaning in this context. The black dwarfs become the permanent monuments of a universe that once, a very long time ago, had stars. The philosophical implications of this are worth sitting with for a moment. We are used to thinking of the universe as a place where things happen. Events occur, time marches forward, change is the norm. But in the black dwarf era, change stops, or more accurately, change becomes so slow, so incremental, that it is effectively non-existent. A black dwarf might experience a quantum fluctuation once every 10 to the 100th power years. A single atom in its lattice might shift position. But that is not change in any meaningful sense. It is just noise, random jitter at the quantum level that has no macroscopic effect. For all practical purposes, the universe has stopped, and it will stay stopped, frozen in this configuration for longer than any number we can comprehend. This raises a question that has no scientific answer, only philosophical ones. If nothing is happening, is time still passing? Does it make sense to talk about the future if the future looks exactly like the present? Does the universe still exist in any way that matters if there is no one to observe it and nothing to observe? There is a concept in cosmology called the observable universe. It is the region of space from which light has had time to reach us since the Big Bang. Currently, the observable universe has a radius of about 46 billion light-years. That is larger than you might expect, because space itself has been expanding while the light was traveling. But the key point is that the observable universe is finite. There are regions of space so far away that their light has not reached us yet. And as the universe continues to expand, and as that expansion accelerates, more and more of the universe will recede beyond the horizon. Galaxies that we can see today will eventually move so far away that their light can no longer reach us, not because they have been destroyed, but because the space between us is expanding faster than light can cross it. In a few 100 billion years, every galaxy outside our local group will have disappeared from view. The observable universe will shrink to just the Milky Way, Andromeda, and a handful of smaller galaxies that are gravitationally bound to us. Everything else will be gone. By the time the black dwarf era arrives, the observable universe will have shrunk even further. The local group of galaxies will have merged into a single, large, elliptical galaxy, and that galaxy will be alone, completely alone. Every other galaxy in the universe will have receded beyond the cosmic horizon. If there were astronomers in this future galaxy looking out into the sky, they would see nothing, no distant galaxies, no quasars, no cosmic microwave background, because it will have redshifted into wavelengths so long that it is effectively undetectable, just darkness. And if those astronomers tried to reconstruct the history of the universe based on what they could observe, they would get it wrong. They would conclude that the universe consists of a single galaxy surrounded by infinite empty space. They would have no way of knowing that there were once billions of other galaxies, no way of detecting the Big Bang, no way of inferring that the universe was ever different than it is now. The expansion of space will have erased the evidence of its own history. This is a sobering thought because it suggests that our current understanding of the universe, the fact that we can observe distant galaxies and measure the cosmic microwave background and reconstruct the timeline of cosmic evolution, is a temporary privilege. We happen to live at a time when the universe is young enough and close enough that we can still see its history, but that window is closing. In a few 100 billion years, the evidence will be gone, and by the black dwarf era, the universe will have become so empty and so cold that any hypothetical observer, if such a thing could exist, would have no way of knowing that it was ever any different. The fact that we can describe all of this, that we can calculate the timeline and predict the properties of black dwarfs and model the black dwarf era with extraordinary precision, despite never having observed a single one of these objects, is one of the more remarkable achievements of theoretical physics. The equations that govern white dwarf cooling are well understood. The thermodynamics are straightforward. The quantum mechanics of electron degeneracy pressure are known. All we have to do is apply those equations over absurdly long timescales, and the predictions fall out naturally. Black dwarfs are not speculative, they are not a guess. They are the inevitable result of processes we can measure and test today. The fact that they do not exist yet does not make them any less real. They are written into the laws of physics. They are as certain as tomorrow's sunrise, just much, much farther away. There is a kind of beauty in that. A reminder that the universe operates according to rules that do not care whether we are watching or whether the outcomes are convenient or comprehensible. The equations do not stop working just because the timelines become absurd. Thermodynamics does not take a break after the stars burn out. Quantum mechanics does not shut down once the universe goes cold. The processes keep running, the clock keeps ticking. And somewhere in the distant future, long after the last human has died, and the last planet has been consumed, and the last star has faded, the universe will settle into its final configuration. A cold, dark, silent expanse filled with black dwarfs, monuments to a time when there was light, fossils of stars that once burned bright enough to create the atoms in your body, reminders that even in a universe heading inexorably toward heat death, toward maximum entropy, toward a state where nothing can ever happen again, the story is not quite over. There are still chapters left to write, even if no one will be around to read them. The black dwarf era is not the end, it is just the longest middle anyone has ever imagined. A period of time so vast that it dwarfs every other era of cosmic history combined. And when it finally ends, if it ends, it will not end with a bang. It will end with the last black dwarf supernova, the final explosion in a universe that has been dark for 10 to the 1000th power years. And after that, silence, true silence, the kind that does not break. The universe will have exhausted its last trick, played its last card, and what comes next, if anything comes next, is beyond even the reach of physics to predict. But for now, for the next few trillion years, the show is still running, the stars are still burning, the light is still here. And we get to watch it, not forever, just for a little while, which, when you think about it, is more than enough. So where does that leave us? Standing here, on a planet orbiting a star that will one day cool into a black dwarf, living in a universe barely old enough to have figured out what black dwarfs even are, staring into a future so distant that calling it the future feels like a category error. We will never see one. No human ever will. The timeline does not allow it. By the time the first black dwarf forms, humanity will have been gone for so long that our entire species, every thought we ever had, every city we ever built, every word we ever spoke, will have been reduced to atoms scattered across a cold, empty cosmos. The Earth will be gone. The Sun will be gone. The Milky Way will have dissolved into a sparse cloud of stellar remnants drifting through a void so vast that distance stops meaning anything. And somewhere in that void, a white dwarf will tick over into darkness, and no one will notice. Because there will be no one left to notice. And yet, we know it will happen. We can describe it. We can calculate when it will happen, how it will behave, what it will look like, even though we will never see it. We can write the equations that govern its cooling, model the crystallization of its core, predict the moment it reaches thermal equilibrium with a universe that has gone colder than anything we can imagine. We can do all of this because the laws of physics do not stop working just because the outcomes are inconvenient or incomprehensible. The universe does not care if we are watching. It just keeps running the equations. Black dwarfs are not the end of the story. They are the story. The long, patient, inevitable conclusion of what happens when you take a star, let it burn, let it die, and then wait. Not for millions of years, not for billions, for quadrillions, for timescales so vast that the entire era of stars, the age we live in right now, the time when the universe is full of light and motion and change, becomes a brief flicker at the very beginning. A momentary spark in a timeline that stretches toward infinity. And maybe that is the point, that we get to be here at all. That we get to live in the universe during its brief, brilliant phase of star formation and galactic structure, when there is still light to see by and warmth to feel and time to wonder what comes next. We are not around for the black dwarf era. We do not get to see the final cooling or the last explosions or the silent monuments drifting